Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's earliest experiments with existence itself. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.5 billion years ago, in the outer spiral arm of an unremarkable galaxy, a laboratory begins to form, not built by hands or designed by minds, but assembled grain by grain from the debris of stellar death. The early Earth coalesces like a slow experiment in planetary chemistry, each meteorite impact adding new variables to an unplanned test of what matter might become when given enough time and pressure. The planet spins molten and orange beneath a black sky unmarked by familiar constellations. Its surface churns with temperatures that would vaporize lead. Yet already the first experimental conditions emerge from chaos. Gravity sorts the heavier elements downward while lighter compounds rise toward what will someday become an atmosphere. The iron sinks deep, forming a core that will generate magnetic fields. The silicates float upward, beginning to cool into the first tentative crusts that crack and reform with each tidal flex from a moon 10 times closer than today's distant companion. This early Earth resembles nothing so much as a vast foundry where cosmic materials undergo their first transformations. The surface remains too hot for solid ground, yet beneath the molten chaos, differentiation proceeds with methodical precision. Elements separate according to their affinities, iron bonding with iron in the depths, oxygen seeking silicon in the rising magmas, sulfur collecting in scattered pools that will someday become ore deposits buried beneath continents not yet conceived. Scientists call this the Hadean Eon, named for the Greek underworld, though nothing about these conditions suggests punishment or torment. Instead, the Earth resembles a planetary-scale laboratory where temperature, pressure, and chemical composition shift in response to bombardment from space. Each incoming asteroid delivers new experimental materials, water ice from the outer solar system, carbon compounds from carbonaceous chondrites, noble gases that will eventually compose the atmosphere's rarest constituents. The bombardment continues for millions of years, each impact momentarily liquefying portions of the surface before allowing them to cool and solidify. Zircon crystals form during these brief, cooling intervals. Tiny time capsules no larger than grains of sand that preserve chemical signatures of Earth's earliest experimental phase. These ancient crystals survive everything that follows, becoming Earth's oldest witnesses to conditions that no longer exist anywhere in the solar system. Some of these zircon grains carry isotopic signatures that suggest liquid water existed much sooner than previous models predicted. Their oxygen isotope ratios hint at interaction with liquid water at temperatures compatible with life, even while the planet's surface remained largely molten. This discovery transforms scientific understanding of the Hadean. What once seemed like an entirely hostile environment may have harbored pockets of moderate conditions where complex chemistry could begin its first tentative experiments. The mystery lingers in the rock record like a quiet question mark etched in crystal structure. How quickly did conditions moderate enough for water to remain stable on the surface? Each zircon crystal holds isotopic ratios that whisper contradictory stories about temperature and atmospheric composition. Some suggest a planet still dominated by impact heating and volcanic outgassing. Others hint at protected environments where water could pool and remain liquid despite the surrounding chaos. The planet somehow cooled faster than thermal models predict, as if the experimental apparatus possessed its own hidden regulatory mechanisms. Perhaps the early atmosphere, thick with water vapor and carbon dioxide, created a greenhouse effect that moderated surface temperatures. Perhaps the frequent impacts, rather than simply heating the surface, actually enhanced cooling by throwing vast amounts of vaporized rock into space. Perhaps the differentiation of Earth's interior proceeded more efficiently than expected, allowing heat to escape through organized convection rather than chaotic churning. Modern geochemists study these ancient zircons under electron microscopes, measuring isotope ratios to parts per million, seeking clues about atmospheric composition and surface temperature 4 billion years ago. Each crystal becomes a microscopic archive of conditions that existed before life, before oceans, before the sun had settled into its current stable output. The ratios of hafnium to lutetium suggest when the first continental crust began to form. The ratios of oxygen isotopes hint at the temperature of ancient waters, yet for every question these crystals answer, they pose 3 more. If liquid water existed so early, where did it collect? If the surface remained largely molten, how did protected environments persist long enough for complex chemistry to develop? If the bombardment continued for hundreds of millions of years, how did any delicate experiments in molecular organization survive the constant disruption? The early Earth spins through its foundational phase with the patient indifference of geological time. Only took 400 million years to build a world from scratch, a duration that encompasses the entire span from the first dinosaurs to today, repeated several times over. Only a few hundred degrees difference between molten hellscape and hospitable laboratory, a margin smaller than the difference between a summer day and winter night compressed into planetary scale. Only the precise distance from a stable star, the exact mass to hold an atmosphere against solar wind, the right mixture of radioactive elements to keep the interior molten without overheating the surface. The universe sets up its most ambitious experiment with the casual precision of deep time, where million-year adjustments register as minor calibrations and 100,000-year volcanic episodes represent brief moments of recalibration. The early bombardment tapers off as the solar system sweeps itself clean of loose debris, leaving behind a planet with the basic infrastructure for more complex experiments. The surface begins to cool and solidify into more stable configurations. In the darkness above the cooling surface, water vapor condenses into droplets that fall as the first rain onto stones still warm from formation. Each raindrop carries dissolved atmospheric gases downward, beginning the chemical reactions that will eventually produce the first soils. The water pools in the lowest places, creating temporary lakes that evaporate and reform as the planet's rotation and emerging weather patterns distribute heat and moisture. These early rains mark the transition from a purely physical experiment in planetary formation to a chemical experiment in surface processes. Water begins its long career as Earth's universal solvent, dissolving minerals from fresh rock and concentrating dissolved substances in temporary pools. The planet's experimental apparatus grows more sophisticated with each cooling cycle. Each rainfall, each tidal interaction with its nearby moon, the Hadean laboratory prepares itself for tests that will run for billions of years, establishing the basic parameters: gravity, magnetic field, atmospheric pressure, surface chemistry that will constrain all future experiments in complexity and organization. The stage assembles itself grain by grain, degree by degree, preparing for the arrival of chemistry sophisticated enough to reproduce itself. The cooling Earth exhales its first experimental atmosphere into the cosmic vacuum, a mixture of gases that bears no resemblance to the air that will someday fill human lungs. Methane rises from volcanic vents in invisible plumes, joining ammonia and hydrogen sulfide in a cocktail that would poison any oxygen-breathing organism. Yet, this toxic blend represents Earth's initial hypothesis about atmospheric chemistry, a reducing environment where electrons flow freely and complex organic molecules can assemble without interference from corrosive oxygen. Water vapor dominates this early atmosphere, creating a thick greenhouse blanket that traps heat from the cooling surface. The planet wraps itself in steam like a laboratory sample under controlled conditions, maintaining temperatures that allow liquid water to exist despite receiving 25% less energy from a younger, dimmer sun. This faint young sun paradox puzzles climatologists. How did early Earth avoid freezing solid when solar luminosity remained so much lower than today's output? The answer lies partly in atmospheric composition and partly in the planet's own internal heat production. Radioactive decay of uranium, thorium, and potassium generates warmth from within, while the thick atmosphere prevents that heat from radiating immediately back to space. Carbon dioxide concentrations may have reached levels hundreds of times higher than today's atmosphere, creating a greenhouse effect powerful enough to compensate for reduced solar heating. The early Earth maintains its experimental temperature through internal chemistry rather than external energy alone. Volcanic outgassing continues to add new components to this atmospheric mixture. Each eruption releases not only lava, but also dissolved gases that have been trapped in magma chambers for millions of years. The composition varies depending on the depth and chemistry of the source. Rock-shallow magmas produce different gas ratios than those rising from the deep mantle. Some volcanoes release primarily water vapor and carbon dioxide. Others contribute significant amounts of sulfur compounds that react with moisture to form acid rain strong enough to dissolve fresh rock within decades. This chemical weathering begins Earth's first large-scale recycling experiment. Acid rain attacks volcanic rock, dissolving minerals and carrying dissolved ions toward the lowest elevations where they concentrate in temporary lakes and seas. The dissolved minerals precipitate out as the water evaporates, forming the first sedimentary deposits. These chemical cycles establish patterns that will persist for billions of years: erosion, transport, concentration, precipitation, burial, uplift, erosion again. The early atmosphere lacks the stratified structure that protects modern Earth from harmful radiation. Without oxygen, no ozone layer forms to filter ultraviolet light from the sun. High-energy photons penetrate all the way to the surface, where they trigger photochemical reactions that would be impossible in today's oxygen-rich environment. Methane molecules absorb ultraviolet radiation and break apart into reactive fragments that recombine into longer hydrocarbon chains. Ammonia undergoes similar transformations, contributing nitrogen-bearing compounds to an increasingly complex atmospheric chemistry. These photochemical processes create Earth's first organic molecules through purely abiotic mechanisms. Simple hydrocarbons form in the upper atmosphere and rain down onto the surface as a dilute organic soup. The chemistry remains far too simple to support life, yet it establishes the basic building blocks that biological systems will eventually co-opt for their own purposes. Carbon chains, nitrogen-bearing molecules, and sulfur-containing compounds accumulate slowly in protected environments where they remain stable for extended periods. Scientists debate whether this early organic chemistry was dominated by formaldehyde-based reactions or hydrogen cyanide pathways. Laboratory experiments suggest both routes could produce amino acids and nucleotide precursors under early Earth conditions, though the relative importance of each pathway remains uncertain. Perhaps both operated simultaneously in different microenvironments, creating multiple parallel experiments in prebiotic chemistry. The mystery of atmospheric evolution deepens when researchers consider how this reducing atmosphere eventually transformed into today's oxygen-rich environment. The transition required not just the evolution of photosynthetic organisms, but also the removal of atmospheric hydrogen to space and the oxidation of dissolved iron in the oceans. Each step in this transformation involved complex feedbacks between atmospheric chemistry, ocean chemistry, and emerging biological processes. Hydrogen escapes most easily to space, being the lightest element and most readily accelerated to escape velocity by solar heating. The early Earth loses hydrogen steadily through this process, gradually shifting atmospheric composition toward more oxidized compounds. Methane and ammonia break down under ultraviolet radiation, releasing hydrogen that drifts away while leaving behind carbon and nitrogen in more complex molecules. This slow atmospheric evolution sets up conditions for the oxygen revolution that will follow billions of years later. Only took several 100 million years to establish stable atmospheric chemistry from scratch, a duration longer than complex life has existed on Earth, compressed into the foundational phase of planetary development. Only required precise balancing between volcanic outgassing and atmospheric escape, between greenhouse warming and radiative cooling, between chemical production and photochemical destruction. Only needed exactly the right planetary mass to retain water vapor while losing excess hydrogen, the right distance from the sun to maintain liquid water despite lower solar luminosity. The early atmosphere drifts through its experimental phase with the patience of geological time, testing different chemical compositions as volcanic activity wanes and photochemical processes mature. Methane concentrations slowly decline as ultraviolet radiation breaks down molecules faster than volcanic processes can replace them. Ammonia similarly decreases, though more gradually due to its greater stability under early Earth conditions. Carbon dioxide persists longer than other atmospheric components, being chemically stable and continuously replenished by volcanic outgassing. Its concentration fluctuates with volcanic activity and weathering rates, creating climate variations that last for millions of years. During periods of intense volcanism, carbon dioxide levels rise and global temperatures increase. During quieter intervals, chemical weathering removes carbon dioxide from the atmosphere faster than volcanoes can replace it, leading to cooler conditions that may occasionally approach freezing. These early climate oscillations represent Earth's first experiments with feedback mechanisms that will eventually regulate global temperature within narrow ranges suitable for life. Chemical weathering proceeds faster at higher temperatures, removing excess carbon dioxide and cooling the planet. Volcanic outgassing increases during periods of tectonic activity, adding carbon dioxide and warming the climate. The balance between these processes establishes Earth's first crude thermostat, though one that operates over timescales of millions rather than thousands of years. The primitive atmosphere continues its chemical evolution as water vapor begins its long journey toward condensation and precipitation. High in the atmosphere, water molecules absorb ultraviolet radiation and break apart into hydrogen and oxygen. The hydrogen escapes to space, while the oxygen atoms recombine with other molecules or remain briefly free as reactive radicals. This photodissociation of water represents one of the earliest sources of oxygen in Earth's atmosphere, though the amounts remain far too small to significantly alter atmospheric chemistry. As the planet's surface continues cooling, water vapor saturation increases and the first substantial rainfalls begin. These early rains differ dramatically from modern precipitation. They fall through an atmosphere lacking oxygen or ozone, carrying dissolved atmospheric gases that create acidic solutions capable of rapidly dissolving fresh rock. The rainwater chemistry varies with atmospheric composition. sometimes rich in dissolved carbon dioxide, sometimes laden with sulfur compounds from recent volcanic eruptions. The bombardment intensifies as Earth's gravitational field sweeps the inner solar system clean of debris, each impact delivering carefully measured doses of experimental materials to the planetary laboratory. Asteroids arrive like cosmic supply shipments. Their cargo holds packed with water ice, organic compounds, and rare elements that local volcanic processes cannot provide. The largest impacts temporarily sterilize vast regions of the surface, while smaller collisions gently deposit their chemical payloads into protected crater lakes where complex reactions can proceed undisturbed. Late heavy bombardment reaches its peak around 4 billion years ago, transforming Earth's surface into a constantly renewed testing ground for impact chemistry. The frequency staggers modern imagination. Major impacts occur every few thousand years, creating crater chains that stretch across entire hemispheres before erosion and volcanism erase the evidence. Each collision releases energy equivalent to millions of nuclear weapons, vaporizing rock and temporarily creating plasma conditions where elements recombine in configurations impossible under normal planetary conditions. These impact events function as planetary-scale chemical reactors, mixing surface materials with incoming meteoritic substances under extreme pressure and temperature. The shock waves compress rock to densities found nowhere else in Earth's crust, creating high-pressure minerals that preserve evidence of ancient impacts in their crystal structures. Coesite and stishovite form only under these extreme conditions, serving as geological fingerprints of cosmic bombardment preserved in rock formations billions of years old. Carbonaceous chondrites deliver Earth's first significant inventory of organic molecules synthesized in the cold vacuum of space. These primitive meteorites contain amino acids, nucleotide bases, and complex hydrocarbons that formed through slow chemical processes in the outer regions of the solar nebula. The organic compounds survive the journey through Earth's atmosphere only in smaller impacts. The larger collisions incinerate everything in fireballs hot enough to vaporize granite. Scientists estimate that impacts during this period delivered organic carbon equivalent to several times the amount currently stored in all living organisms. Most of this material underwent immediate thermal decomposition upon impact, but some fractions survived in protected environments or underwent transformation into new organic compounds under impact-generated pressure and heat. These impact-processed organics may have provided crucial building blocks for prebiotic chemistry, though the exact mechanisms remain poorly understood. The bombardment also delivers vast quantities of water to supplement whatever moisture survived from Earth's initial formation. Comets from the outer solar system carry isotopically distinct water that mixes with indigenous terrestrial water, creating chemical signatures that persist in modern ocean composition. The ratio of deuterium to hydrogen in Earth's oceans reflects this ancient mixing of water sources. Though debate continues over the relative contributions from comets versus asteroidal impacts, each major impact temporarily disrupts existing surface conditions while simultaneously creating new experimental environments. The largest collisions excavate craters hundreds of kilometers across, exposing deep crustal rocks to surface weathering while creating central uplifts that concentrate rare minerals in accessible locations. The impact-generated heat drives hydrothermal circulation systems that operate for thousands of years after each collision, creating chemical gradients where dissolved minerals precipitate in complex patterns. These hydrothermal systems represent some of Earth's earliest experiments in geochemical cycling. Hot water circulation dissolves minerals from the crater walls and transports them through underground networks before depositing concentrated solutions in surface pools. The chemistry varies depending on the composition of impact-fractured bedrock. Some systems become rich in sulfur compounds. Others concentrate metals like iron and nickel. Still others create unusual alkaline conditions where carbon dioxide converts to carbonate minerals. The mystery of bombardment timing puzzles planetary scientists who study the distribution of impact ages across the inner solar system. The late heavy bombardment appears to have affected all terrestrial planets simultaneously, suggesting a solar system-wide disruption rather than gradual cleanup of primordial debris. Perhaps the migration of Jupiter and Saturn destabilized asteroid orbits, sending swarms of rocky bodies careening toward the inner planets. Perhaps the disruption of a large asteroid family created the concentrated bombardment that left its signature on lunar highlands and Martian crustal rocks. Alternative models propose that the bombardment represents normal tail-end accretion stretched over hundreds of millions of years rather than a discrete period of intensified impacts. The apparent clustering of impact ages might reflect sampling bias in the lunar rock collection or selective preservation of impact signatures from a particular time period. Each new meteorite sample and each improved dating technique refines understanding of bombardment chronology, though fundamental questions about timing and causes remain unresolved. Only took a few 100 million years to sweep the solar system mostly clean of impact hazards, a cleanup operation that delivered more water and organic compounds to Earth than all subsequent geological processes combined. Only required gravitational perturbations to redirect asteroid orbits from stable configurations toward planet-crossing trajectories, transforming peaceful debris fields into cosmic artillery barrages. Only needed precise timing to deliver crucial materials after planetary surfaces had cooled enough to preserve complex chemistry, but before life required stable conditions for establishment. The bombardment tapers off gradually as the supply of large projectiles dwindles and gravitational dynamics settle into more stable configurations. Impact rates decline by orders of magnitude, transitioning from frequent major collisions to the occasional asteroid or comet encounter that characterizes the modern era. This transition marks the end of Earth's most violent experimental phase and the beginning of more subtle chemical evolution. The surface bears countless scars from this cosmic bombardment, though subsequent geological activity erases most impact structures within a few 100 million years. Only the largest crater systems survive long enough to influence subsequent geological evolution. The Sudbury Basin in Canada preserves evidence of an impact so massive it fractured the crust to depths of several kilometers, creating mining districts that concentrate nickel and platinum group elements in economically recoverable deposits. Smaller impacts continue to deliver trace amounts of extraterrestrial material throughout Earth's history, maintaining a slow but steady input of cosmic chemistry to surface environments. Micrometeorites rain down constantly, contributing dust-sized particles rich in rare elements like iridium and osmium that become incorporated into sedimentary rocks. These cosmic signatures allow geochemists to track the rate of extraterrestrial material input over geological time, revealing periods of enhanced bombardment associated with comet showers or asteroid family disruptions. The impact-generated heating and chemical mixing establishes new baselines for crustal composition and volatile inventories. Each major collision redistributes elements according to their chemical affinities under extreme conditions, creating ore deposits and unusual mineral assemblages that would not form through normal igneous or sedimentary processes. The pressure and temperature conditions during impact exceed those found in most terrestrial environments, enabling formation of diamond, high-pressure silicate polymorphs, and exotic mineral phases that provide unique insights into deep Earth conditions. As the bombardment wanes, Earth's experimental apparatus grows more sophisticated through the accumulation of diverse materials and the establishment of stable surface environments. The planet's chemical inventory now includes water sufficient to fill ocean basins, organic compounds complex enough to support prebiotic chemistry, and crustal heterogeneity that creates diverse microenvironments for chemical experimentation. The stage has been set for more delicate tests involving molecular organization and self-replication. The cosmic supply ships continue their occasional deliveries, but now the intervals between major impacts stretch to millions or tens of millions of years. Earth's laboratory enters a quieter phase where internal processes dominate over external perturbations, allowing time for careful chemical experiments that require stable conditions to reach completion. The first oceans accumulate drop by drop as the planet's fever breaks and water vapor condenses from the steaming atmosphere. These primordial seas bear no resemblance to today's blue expanses. They simmer at temperatures that would boil modern marine life, their chemistry dominated by dissolved volcanic gases and impact-delivered salts that create bitter, acidic broths unfit for any organism yet conceived. Yet, these scalding pools represent Earth's first great chemical reactors. Vast beakers where dissolved minerals concentrate and interact in combinations impossible on a dry planetary surface. Water gathers in the lowest elevations with the patient persistence of gravity, flowing downhill from impact craters and volcanic highlands toward broad basins that will eventually become ocean floors. The early topography remains crude and unstable. Fresh lava flows constantly reshape drainage patterns, while ongoing impacts temporarily vaporize entire water bodies before allowing them to reform in slightly different configurations. The ocean basins shift and change location as the primitive crust founders and reforms under the weight of accumulated water and sediment. The chemistry of these early seas reflects their violent origins and chaotic inputs. Dissolved chlorine from volcanic outgassing combines with sodium weathered from fresh basaltic rocks to create concentrated brines many times saltier than modern seawater. Iron dissolved from impact-shattered bedrock gives the water a rust-red coloration that deepens with each fresh meteorite delivery. Sulfur compounds from hydrothermal vents create acidic conditions that dissolve carbonate minerals as quickly as they form, preventing the buffering reactions that stabilize modern ocean chemistry. Temperature profiles in these primordial oceans vary dramatically with depth and location. Surface waters reach temperatures approaching the boiling point of pure water, heated by the greenhouse atmosphere and ongoing volcanic activity. Deeper regions remain cooler, but still hot enough to prevent most modern organisms from surviving more than minutes. Hydrothermal circulation patterns distribute heat unevenly, creating temperature gradients that drive chemical reactions impossible under uniform conditions. These thermal gradients establish Earth's first experiments in convective mixing and chemical stratification. Hot water rises from hydrothermal sources, carrying dissolved minerals toward the surface where they precipitate as temperatures drop and chemical conditions change. Cold, dense brines sink toward the seafloor, concentrating dissolved salts and creating density layers that resist mixing. The circulation patterns create chemical microenvironments where specific reactions can proceed, oxidizing conditions near the surface, reducing environments in the depths, neutral zones at intermediate depths where different chemical pathways compete. Scientists studying fluid inclusions in ancient rocks find evidence that these early oceans contained dissolved chloride concentrations up to 10 times higher than modern seawater. The high salinity reflects rapid evaporation from hot surface waters and the lack of continental weathering to dilute marine chemistry with freshwater runoff. Only scattered volcanic islands provided solid surfaces above water level, creating tiny pockets of subaerial chemistry isolated from the vast oceanic laboratory. The mystery of early ocean volume puzzles geochemists who model water cycling on the hot early Earth. Atmospheric water vapor concentrations may have reached saturation levels impossible under current conditions, creating a steam atmosphere that contained several times more water than all modern oceans combined. As surface temperatures dropped below critical thresholds, this atmospheric reservoir precipitated rapidly, creating deluges that lasted for thousands of years and filled ocean basins to depths exceeding those found anywhere on modern Earth. Alternative models suggest that early oceans underwent repeated cycles of evaporation and condensation as surface temperatures fluctuated with volcanic activity and impact heating. Each major collision would have vaporized surface water across continental scales, temporarily returning vast quantities of moisture to the atmosphere before allowing it to recondense as temperatures dropped. These evaporation-condensation cycles would have concentrated dissolved minerals in surviving water bodies while redistributing fresh water to new locations. The chemical evolution of seawater composition reflects the changing balance between inputs from volcanic outgassing, hydrothermal circulation, impact delivery, and chemical weathering of exposed rocks. Early oceans received proportionally more input from internal sources, volcanism and hydrothermal activity, compared to external sources like atmospheric precipitation and surface runoff. This creates chemical signatures distinct from modern seawater, with elevated concentrations of elements like iron, sulfur, and dissolved silica that reflect high-temperature equilibrium with basaltic rocks. Hydrothermal vents begin their billion-year career as centers of chemical innovation, creating steep gradients in temperature, pH, and dissolved species that drive complex reaction networks. The hot springs discharge fluids superheated to several hundred degrees, carrying dissolved metals and sulfur compounds that precipitate immediately upon contact with cooler seawater. These precipitation reactions create mineral chimneys that grow upward from the seafloor like chemical gardens, their internal plumbing systems creating countless microenvironments where different chemical experiments can proceed simultaneously. The mineral deposits around hydrothermal vents concentrate rare elements that remain dispersed at low concentrations in average seawater. Copper, zinc, lead, and precious metals precipitate from hydrothermal fluids, creating ore deposits that will eventually be uplifted and exposed by tectonic processes. The chemical signatures of these ancient seafloor deposits preserve records of early ocean chemistry, though interpreting these signatures requires careful consideration of post-depositional alteration and metamorphic overprinting. Only took several 100 million years to fill ocean basins from a nearly dry planet, a transition that required precise balancing between water input from volcanism and impacts versus water loss through atmospheric escape and chemical incorporation into hydrated minerals. Only needed exactly the right surface temperature to allow liquid water stability while maintaining high enough vapor pressure to drive rapid hydrological cycling. Only required gravitational and atmospheric conditions that prevented complete water loss to space while allowing sufficient atmospheric residence time for chemical equilibration. The early oceans churned through their chemical evolution with the methodical persistence of planetary scale reactions operating over geological timescales. Evaporation concentrates dissolved substances in residual brines, while precipitation removes supersaturated species from solution. Chemical weathering of volcanic rocks adds fresh dissolved loads, while hydrothermal circulation recycles seawater through hot crustal rock, where mineral equilibration modifies dissolved chemistry. The salinity and chemical composition of seawater stabilize gradually as the balance between inputs and outputs reaches dynamic equilibrium. The most soluble species, sodium and chloride, accumulate to concentrations limited primarily by evaporation rates and precipitation of salt minerals in restricted basins. Less soluble elements like silica and iron maintain lower concentrations controlled by chemical equilibria with seafloor sediments and hydrothermal mineral deposits. These chemical equilibria establish the baseline ocean chemistry that will persist through subsequent geological evolution, though with important modifications as atmospheric oxygen concentrations increase and biological processes begin to influence marine chemistry. The early oceans create stable chemical conditions suitable for more complex experimentation while maintaining enough environmental variability to support diverse reaction pathways. Chemical zonation develops both vertically and horizontally as ocean circulation patterns establish distinct water masses with characteristic temperature and chemical signatures. Surface waters maintain different chemistry from deep waters due to differential heating, evaporation, and chemical exchange with the atmosphere. Coastal waters near volcanic islands develop chemistry distinct from open ocean conditions due to enhanced inputs from sub-aerial weathering and hydrothermal activity. The vast oceanic laboratory establishes its basic operating parameters through millions of years of chemical trial and error, testing different combinations of temperature, pressure, pH, and dissolved chemistry until stable configurations emerge. These stable chemical environments provide the reaction vessels where more sophisticated experiments in molecular organization can begin their tentative exploration of complexity and cooperation. The first stromatolites begin to appear along shallow coastlines as Earth's most patient experimenters establish their colonies in the intertidal zones. These layered mounds of sediment and microbial mats represent something unprecedented in the planet's 4 billion-year history, structures built not by physical processes alone, but by the metabolic activities of living organisms. Cyanobacteria trap sediment grains between their sticky filaments during each tidal cycle, creating paper-thin layers that accumulate into dome-shaped monuments to biological persistence. Each stromatolite grows upward at the pace of geological patience, adding perhaps a few millimeters of height per year as successive generations of bacteria bind sediment particles into coherent structures. The layered architecture preserves a day-by-day record of ancient environmental conditions. Storm deposits create thicker layers, while calm periods produce finer laminations. Seasonal variations in bacterial growth rates create subtle rhythmic patterns that allow paleontologists to calculate the length of ancient days and years from billion-year-old rocks. These microbial cities represent Earth's first large-scale engineering projects. Though the engineers measure only a few micrometers in length and lack any central planning authority, individual cyanobacteria follow simple rules: swim toward light, avoid toxic chemicals, reproduce when conditions allow, yet their collective behavior creates complex three-dimensional structures that persist for millions of years. The emergent architecture resembles nothing so much as vast urban sprawls built by microscopic inhabitants who never intended to create monuments. The cyanobacteria themselves conduct Earth's most revolutionary chemical experiment, photosynthesis. These tiny organisms capture sunlight and use its energy to split water molecules, combining the resulting hydrogen with carbon dioxide to manufacture organic compounds while releasing oxygen as a waste product. The process seems deceptively simple, yet it requires sophisticated molecular machinery that coordinates dozens of chemical reactions with precise timing and spatial organization. Scientists study modern stromatolites in Shark Bay, Australia, and the Bahamas to understand how these ancient structures formed and functioned. The living microbial mats exhibit complex vertical zonation, with different bacterial species occupying distinct layers based on their tolerance for oxygen, light intensity, and chemical conditions. Cyanobacteria dominate the surface layers where photosynthesis occurs most efficiently. Purple bacteria occupy intermediate depths where they conduct photosynthesis using longer wavelengths that penetrate through the upper layers. Sulfate-reducing bacteria thrive in the oxygen-free depths where they process organic matter and produce hydrogen sulfide. This vertical stratification creates chemical gradients that drive complex cycling of carbon, sulfur, and nitrogen compounds within the microbial mat ecosystem. Oxygen produced by surface photosynthesis diffuses downward until bacterial respiration consumes it completely. Hydrogen sulfide produced in the depths migrates upward until it reaches layers where sulfur-oxidizing bacteria convert it back to sulfate. These chemical cycles operate on timescales ranging from hours to seasons, creating dynamic equilibria that maintain stable community structure over geological timescales. The mystery of photosynthesis evolution challenges biochemists who attempt to understand how such complex molecular machinery could have assembled through gradual evolutionary processes. The photosynthetic apparatus requires dozens of precisely coordinated proteins, including specialized chlorophyll molecules that capture light energy and transfer it through electron transport chains with quantum mechanical efficiency. Each component appears essential for function, raising questions about how intermediate stages could have provided sufficient advantage to drive natural selection. Recent research suggests that photosynthesis may have evolved through the combination of simpler metabolic pathways that originally served other functions. Some bacteria use similar electron transport chains for respiration in the absence of oxygen. Others employ light-harvesting pigments for protection against harmful radiation rather than energy capture. The merger of these existing systems could have created functional photosynthetic machinery without requiring simultaneous evolution of all components from scratch. The timing of photosynthesis evolution remains contentious among researchers who study isotopic signatures in ancient rocks. Some chemical evidence suggests that oxygen-producing photosynthesis began as early as 3.8 billion years ago, shortly after the first evidence for life appears in the geological record. Other interpretations favor a later origin around 2.7 billion years ago, closer to the time when atmospheric oxygen concentrations began their dramatic rise. The discrepancy may reflect the difference between the initial evolution of photosynthesis and its subsequent ecological dominance. Stromatolites preserve some of the most ancient evidence for biological activity on Earth, though interpreting these structures requires careful consideration of abiotic processes that can create similar layered morphologies. Chemical precipitation from hydrothermal fluids occasionally produces laminated deposits that superficially resemble biological stromatolites. Sedimentary processes in shallow water environments can create rhythmic layering through purely physical mechanisms. Only detailed microscopic examination and geochemical analysis can distinguish definitively between biological and abiotic origins. Only took a few billion years for microscopic organisms to begin construction projects visible from aircraft altitude architectural achievements that dwarf human engineering efforts in both scale and longevity. Only required the invention of molecular machinery sophisticated enough to capture sunlight and convert carbon dioxide into organic matter, a process that modern technology cannot replicate with comparable efficiency. Only needed precisely the right environmental conditions to support photosynthesis while providing stable substrates for stromatolite construction. The stromatolite builders conduct their experiments in community organization with the methodical persistence of bacterial reproduction operating over geological timescales. Each generation inherits slightly modified chemical conditions created by the metabolic activities of previous generations. Oxygen production gradually alters local chemistry, while organic matter accumulation provides new resources for diverse bacterial communities. The evolutionary feedback operates so slowly that thousands of generations pass before environmental changes become significant enough to influence natural selection. These ancient microbial ecosystems establish Earth's first experiments in ecosystem engineering, the modification of environmental conditions by organisms in ways that influence their own survival and reproduction. Cyanobacteria create oxygen-rich microenvironments that exclude competing bacteria while providing habitat for oxygen-tolerant species. Their organic matter production supports complex food webs of heterotrophic bacteria that recycle nutrients and maintain chemical cycles essential for continued photosynthesis. The chemical signatures preserved in stromatolite rocks provide direct evidence for biological activity extending back nearly 3.5 billion years. Isotopic ratios of carbon in organic matter reflect the biochemical processes used by ancient organisms to incorporate carbon dioxide into cellular components. The ratios differ distinctly from those produced by abiotic chemical reactions, creating definitive fingerprints of biological activity that survive metamorphism and weathering over geological timescales. Trace element concentrations in stromatolite carbonates record ancient ocean chemistry and atmospheric composition during the time of deposition. Rare earth element patterns reflect the oxidation state of seawater and the availability of dissolved nutrients essential for bacterial growth. Sulfur isotope ratios preserve information about ancient atmospheric oxygen levels and the bacterial processes that cycled sulfur compounds through early marine ecosystems. The global distribution of stromatolite deposits indicates that photosynthetic bacteria colonized diverse marine environments during the Archean and Proterozoic eras. Fossil stromatolites occur on every continent, suggesting that microbial mat ecosystems dominated shallow marine environments for over 2 billion years. The structures reached maximum diversity and abundance during the Proterozoic era before declining as grazing organisms evolved and began consuming microbial mats faster than they could grow. Modern stromatolites persist only in extreme environments where harsh chemical conditions exclude grazing organisms that would otherwise destroy the microbial mats. The living structures provide natural laboratories for studying ancient microbial processes and testing hypotheses about early life on Earth. Each modern stromatolite represents a continuation of biological processes that began billions of years ago, maintaining direct experimental connections to Earth's earliest ecosystems. Oxygen accumulates in Earth's atmosphere like a slow-acting poison, transforming the planet's chemistry with patient lethality that operates over hundreds of millions of years. The Great Oxygenation Event begins innocuously around 2.4 billion years ago as cyanobacteria continue their photosynthetic experiments, splitting water molecules and releasing oxygen gas as metabolic waste. For the anaerobic organisms that have dominated Earth's biosphere for over 1 billion years, this oxygen represents a corrosive toxin that destroys cellular machinery and makes previously habitable environments uninhabitable. The transition proceeds with geological gradualism. Oxygen concentrations rising from essentially 0 to perhaps 1% of modern atmospheric levels over a span of time that encompasses hundreds of millions of bacterial generations. This seemingly modest increase fundamentally alters the chemical environment of Earth's surface, oxidizing dissolved iron in the oceans and creating the banded iron formations that preserve evidence of this atmospheric revolution in sedimentary rocks scattered across every continent. Red and black stripes alternate through thousands of meters of ancient seafloor deposits, each layer recording the seasonal or cyclical variations in oxygen production and iron oxidation that characterize this transitional period. The red layers contain oxidized iron minerals that could form only in the presence of dissolved oxygen. The black layers preserve reduced iron compounds deposited when oxygen levels dropped below critical thresholds for iron oxidation. These banded iron formations represent Earth's most extensive chemical archives, documenting century-by-century fluctuations in atmospheric composition during the planet's most dramatic geochemical transition. The iron formations require precise chemical conditions that no longer exist anywhere on modern Earth. Ocean water must contain high concentrations of dissolved iron while maintaining low enough oxygen levels to prevent immediate precipitation of iron oxides in the water column. Seasonal blooms of cyanobacteria produce pulses of oxygen that trigger episodic iron oxidation, creating the rhythmic banding that characterizes these ancient deposits. The delicate balance between iron supply and oxygen production creates chemical conditions that persist for only a few 100 million years before evolving beyond the narrow stability field required for banded iron formation. This oxygenation represents Earth's first global pollution crisis, though the pollutant becomes essential for all complex life that follows. Oxygen reacts aggressively with organic molecules, breaking chemical bonds and generating reactive oxygen species that damage cellular components. Anaerobic bacteria experience this oxidative stress as a catastrophic environmental change that eliminates previously successful metabolic strategies while creating opportunities for organisms capable of tolerating or utilizing the toxic new atmospheric component. The biochemical innovation of oxygen tolerance requires sophisticated cellular machinery to neutralize reactive oxygen species before they destroy essential biological molecules. Antioxidant enzymes like catalase and superoxide dismutase evolve to decompose hydrogen peroxide and other oxygen radicals that form spontaneously in oxygen-rich environments. These protective mechanisms represent some of biology's most complex molecular machines, employing transition metals like iron and manganese in precisely coordinated catalytic reactions. Scientists debate whether the Great Oxygenation Event represents a gradual increase in oxygen production by evolving cyanobacteria or a sudden change in atmospheric chemistry triggered by the exhaustion of chemical sinks that previously consumed oxygen as quickly as it formed. The consumption model suggests that early oxygen production proceeded for hundreds of millions of years without atmospheric accumulation because dissolved iron, sulfur compounds, and organic matter in ocean water reacted with oxygen faster than photosynthesis could produce it. The timing coincides with geological evidence for changes in crustal composition and tectonic processes that could have influenced the global oxygen budget. Increased continental weathering rates would have delivered more nutrients to marine ecosystems, while simultaneously increasing the flux of reduced minerals that consume oxygen through chemical reactions. Changes in hydrothermal circulation patterns could have altered the supply of reduced chemicals from deep ocean sources. The interplay between geological and biological processes creates complex feedbacks that determine the timing and rate of atmospheric oxygenation. The mystery of oxygen accumulation deepens when researchers consider the isotopic evidence preserved in ancient sulfur minerals. Mass-independent sulfur isotope fractionation occurs only in atmospheres containing less than 1 part per million oxygen, creating distinctive chemical signatures that disappear abruptly from the geological record around 2.4 billion years ago. This isotopic transition provides precise timing for atmospheric oxygenation while raising questions about the mechanisms that triggered such rapid chemical change. Alternative explanations invoke changes in atmospheric hydrogen concentrations or variations in ultraviolet radiation intensity that could have influenced sulfur isotope chemistry without requiring specific oxygen thresholds. The hydrogen escape model suggests that atmospheric oxygenation resulted primarily from hydrogen loss to space rather than increased oxygen production, with photochemical processes gradually shifting atmospheric composition toward more oxidized species. Each model makes different predictions about trace gas concentrations and isotopic signatures that can be tested against geological evidence. Only took a few 100 million years to transform Earth's atmosphere from reducing to oxidizing a chemical revolution that required precise coordination between biological oxygen production and geological oxygen consumption to maintain environmental conditions suitable for continued evolution. Only needed exactly the right balance between photosynthetic activity and chemical weathering rates to prevent runaway atmospheric changes that could have sterilized the planet through extreme oxidation or reduction. Only required evolutionary innovations sophisticated enough to protect cellular machinery from oxidative damage while developing new metabolic pathways that could exploit oxygen as an energy source. The Great Oxygenation Event proceeds through its transformative phase with the methodical persistence of geochemical processes operating over timescales that dwarf human comprehension. Oxygen concentrations fluctuate dramatically as biological production rates vary with environmental conditions and nutrient availability. Glacial periods reduce photosynthetic activity and allow atmospheric oxygen to decline through reaction with exposed organic matter. Warmer intervals enhance cyanobacterial growth and drive oxygen levels toward higher concentrations that begin to approach modern atmospheric values. These oscillations create selection pressures that drive rapid evolution of oxygen metabolism in diverse bacterial lineages. Some organisms develop sophisticated electron transport chains that use oxygen as a terminal electron acceptor, extracting far more energy from organic compounds than anaerobic metabolism can provide. Others evolve protective mechanisms that allow survival in oxygen-rich environments without necessarily exploiting oxygen for energy production. Still, others retreat to oxygen-free refugia, where ancient metabolic strategies remain viable for billions of years. The chemical consequences of atmospheric oxygenation extend far beyond biological systems to influence weathering rates, mineral stability, and global elemental cycles. Oxygen exposure accelerates the breakdown of reduced minerals in surface rocks, increasing the supply of dissolved nutrients to marine ecosystems while simultaneously creating oxidized mineral assemblages that remain stable under surface conditions. Iron-bearing minerals undergo systematic transformation from reduced phases like pyrite and magnetite to oxidized phases like hematite and goethite. This oxidative weathering fundamentally alters the chemical composition of sediments transported from continental areas to marine depositional environments. River waters carry higher concentrations of dissolved sulfate, nitrate, and oxidized trace metals that create new chemical niches for specialized bacterial communities. The enhanced nutrient supply supports increased biological productivity, while the changing chemical conditions eliminate some metabolic strategies and promote others. Ocean chemistry evolves in response to changing atmospheric composition as dissolved oxygen concentrations increase gradually from essentially zero toward levels that begin to support aerobic respiration throughout the water column. The transition creates chemical gradients that persist for hundreds of millions of years as deep ocean circulation slowly equilibrates with atmospheric oxygen concentrations. Surface waters achieve oxygen saturation relatively quickly, while deep waters remain anoxic until circulation patterns distribute oxygenated water to abyssal depths. The oxygenation of seawater triggers complex changes in marine biogeochemical cycles as aerobic and anaerobic processes compete for organic substrates and electron acceptors. Sulfate reduction becomes restricted to sedimentary environments, where organic matter consumption depletes dissolved oxygen concentrations below levels required for aerobic respiration. Nitrate cycling develops new pathways, as oxygen availability enables nitrogen oxidation reactions that were impossible under reducing conditions. These marine chemical changes establish the foundation for more complex ecosystems that will exploit the higher energy yields available through aerobic metabolism while maintaining the biogeochemical cycles essential for continued productivity in marine environments. The first cellular partnerships form through accidents that become permanent arrangements. As one bacterium engulfs another in what appears to be an act of predation, but evolves into the most successful collaboration in the history of life. Endosymbiosis begins when a primitive eukaryotic cell attempts to consume an aerobic bacterium, but fails to digest its prey completely. The bacterium survives inside its host's cytoplasm, continuing to respire and produce energy while receiving protection and nutrients from the larger cell. This partnership proves so advantageous that both organisms lose the ability to survive independently, creating the first organelles through biological merger rather than gradual evolutionary modification. The engulfed bacteria become mitochondria, retaining their own circular DNA and double membrane structure while specializing in energy production for their host cells. These cellular power plants process organic molecules through aerobic respiration, generating far more energy than anaerobic metabolism can provide. The arrangement allows eukaryotic cells to grow larger and more complex than their bacterial predecessors, while maintaining efficient energy production despite increased cellular volumes and metabolic demands. Lynn Margulis first proposed this endosymbiotic theory in the 1960s, facing skepticism from biologists who preferred gradual evolutionary explanations over sudden cellular mergers. The evidence for ancient endosymbiosis has since become overwhelming. Mitochondrial DNA sequences clearly indicate bacterial ancestry, while electron microscopy reveals structural similarities between mitochondria and free-living bacterial cells. Phylogenetic analysis suggests that mitochondria derived from alpha proteobacteria related to modern rickettsia. Intracellular parasites that maintain similar relationships with contemporary host cells. The timing of mitochondrial acquisition coincides roughly with the Great Oxygenation event, suggesting that aerobic respiration provided crucial advantages for surviving in newly oxygenated environments. Cells equipped with mitochondria could not only tolerate oxygen exposure, but actually exploit this formerly toxic gas for enhanced energy production. The partnership allowed rapid expansion into ecological niches that remained inaccessible to anaerobic organisms, while providing energy resources for developing more sophisticated cellular structures and processes. A second endosymbiotic event creates chloroplasts when early eukaryotic cells engulf cyanobacteria and establish permanent photosynthetic partnerships. Like mitochondria, chloroplasts retain vestiges of their bacterial origins, circular DNA, double membranes, and molecular machinery similar to their free-living relatives. Some algae contain chloroplasts that clearly derive from multiple independent endosymbiotic events, creating cells within cells within cells in arrangements that resemble nested Russian dolls more than conventional biological organization. The chloroplast endosymbiosis enables eukaryotic cells to conduct photosynthesis while maintaining the complex internal organization that distinguishes them from bacterial cells. This combination proves extraordinarily successful, leading to the diversification of algae and eventually to the evolution of land plants that will transform terrestrial environments. The partnership allows photosynthetic eukaryotes to grow much larger than cyanobacteria while maintaining efficient light capture and carbon fixation. Scientists study modern examples of endosymbiosis to understand how these ancient cellular partnerships might have evolved and stabilized. Some amoeba contain bacterial endosymbionts that have become essential for host survival, though the relationships remain less integrated than those seen in mitochondria and chloroplasts. The bacterium Buchnera lives exclusively inside aphid cells, providing essential amino acids that the insects cannot synthesize themselves. These contemporary examples suggest that endosymbiosis represents an ongoing evolutionary process rather than a historical curiosity. The biochemical integration between endosymbionts and their hosts requires extensive coordination of cellular processes that operate on different timescales and respond to different environmental cues. Mitochondria must increase their respiratory activity when host cells demand more energy, while chloroplasts must adjust their photosynthetic output to match light availability and carbon dioxide concentrations. This coordination requires complex signaling systems that allow organelles to communicate with their host cells and vice versa. The mystery of endosymbiotic gene transfer puzzles molecular biologists who study the evolutionary transition from independent organisms to integrated organelles. Most genes originally present in endosymbiotic bacteria have migrated to the host cell nucleus over evolutionary time, leaving organelles with drastically reduced genomes that encode only the most essential functions. This gene transfer requires precise coordination to maintain functional protein complexes that span multiple cellular compartments. Mitochondria in modern eukaryotes retain only a few dozen genes compared to the thousands present in their free-living bacterial relatives. The transferred genes must acquire new regulatory sequences that respond to eukaryotic cellular signals while maintaining their original biochemical functions. Some proteins encoded by nuclear genes must be imported back into mitochondria after synthesis, requiring sophisticated targeting signals and transport machinery that did not exist in the original bacterial endosymbionts. The process of organelle genome reduction continues in contemporary endosymbiotic relationships, allowing researchers to observe intermediate stages in the transition from independent bacteria to integrated organelles. Some endosymbionts have lost the ability to synthesize cell walls or reproduce independently while retaining larger genomes than typical organelles. Others maintain intermediate levels of genetic autonomy that provide insights into the evolutionary pressures driving genome reduction and gene transfer. Only took a few 100 million years to transform independent bacterial cells into essential organelles through accidental partnerships that became permanent arrangements, evolutionary innovations that required precise biochemical coordination between organisms with fundamentally different cellular organizations, only needed exactly the right environmental conditions to favor cellular cooperation over competition, allowing temporary associations to evolve into obligate partnerships that neither participant can survive without. Only required genetic mechanisms sophisticated enough to coordinate gene expression and protein transport across multiple cellular compartments while maintaining the biochemical specialization that makes organelles useful to their hosts. The endosymbiotic partnerships mature through their evolutionary integration with the methodical persistence of natural selection operating over millions of generations. Each minor improvement in biochemical coordination provides slight advantages that accumulate into major differences in cellular efficiency and environmental tolerance. Host cells evolve mechanisms for controlling organelle reproduction and metabolism, while organelles develop increased dependence on host-provided resources and protection. These cellular collaborations establish new levels of biological organization that transcend the traditional boundaries between individual organisms. Eukaryotic cells represent composite entities whose evolutionary success depends on maintaining cooperation between genetically distinct components with partially conflicting interests. The resulting cellular architectures prove remarkably stable over evolutionary time while remaining flexible enough to support continued diversification and specialization. The biochemical consequences of endosymbiosis extend beyond energy production and photosynthesis to influence every aspect of eukaryotic cellular metabolism. Mitochondria become essential for synthesizing iron-sulfur clusters and heme groups required for electron transport in diverse metabolic pathways. Chloroplasts provide not only photosynthetic capacity, but also biosynthetic machinery for producing amino acids, fatty acids, and other organic compounds essential for plant growth and development. The spatial organization of eukaryotic cells reflects their endosymbiotic origins, as organelles maintain physical separation from cytoplasmic processes while participating in integrated metabolic networks. This compartmentalization allows incompatible chemical reactions to proceed simultaneously within the same cell while maintaining precise control over metabolic flux and energy distribution. The resulting cellular architectures support much higher levels of metabolic complexity than possible in prokaryotic cells. Organella inheritance patterns create unique genetic phenomena that influence eukaryotic evolution in ways impossible for organisms with single chromosomal systems. Mitochondria and chloroplasts typically inherit maternally, creating genetic bottlenecks that reduce organella genetic diversity while allowing rapid fixation of beneficial mutations. These inheritance patterns contribute to reproductive isolation between populations and influence the evolution of sexual reproduction and mating systems. The endosymbiotic partnerships establish the cellular foundation for all complex life that follows, creating energy production systems and metabolic capabilities that will support the evolution of multicellular organisms, complex tissues, and eventually conscious beings capable of understanding their own endosymbiotic origins. Ice encases the planet in crystalline silence as Earth experiments with its most extreme climate state, freezing solid from poles to equator in a global refrigeration that lasts for millions of years. Snowball Earth episodes occur at least twice during the Proterozoic era, transforming the blue planet into a white sphere that reflects sunlight back to space with mirror-like efficiency. The ice sheets extend from continental highlands down to sea level and beyond, creating frozen oceans that reach thicknesses of several kilometers while isolating marine ecosystems beneath an impenetrable ceiling of solid water. The transition into global glaciation proceeds through positive feedback mechanisms that accelerate once ice coverage reaches critical thresholds. Fresh snow and ice reflect up to 90% of incoming solar radiation compared to the 30% reflected by typical ocean surfaces. As ice coverage expands from polar regions toward lower latitudes, the planet's albedo increases dramatically, reducing the amount of solar energy absorbed by surface materials and driving temperatures even lower. The cooling promotes additional ice formation, creating a runaway process that continues until ice reaches the equator. Geological evidence for these extreme glacial periods comes from dropstones and glacial striations found in rock formations that originated near ancient equatorial latitudes. Dropstones represent boulders carried by glacial ice and dropped into marine sediments when the ice melted, creating anomalous coarse-grained rocks scattered through otherwise fine-grained sedimentary sequences. The striations preserve scratches carved into bedrock by moving glaciers, their orientations indicating ice flow directions that extend far beyond the polar regions where glaciation typically occurs. The carbon isotope signatures in sedimentary rocks deposited during snowball episodes show dramatic excursions that reflect the collapse of global carbon cycling. Photosynthesis nearly ceases when ice blocks sunlight from reaching marine ecosystems, causing atmospheric carbon dioxide concentrations to rise as volcanic outgassing continues without biological consumption. The isotopic ratios preserve evidence for this disruption of normal biogeochemical cycles, creating distinctive chemical signatures that mark the onset and termination of global glacial periods. Climate models suggest that once global glaciation begins, surface temperatures drop to -40 degrees Celsius even at equatorial latitudes. These extreme conditions would freeze carbon dioxide out of the atmosphere at polar latitudes, creating dry ice deposits that sublimate directly from solid to vapor as seasonal temperatures fluctuate. The frozen planet resembles contemporary Mars more than modern Earth, with thin atmospheres dominated by water vapor and carbon dioxide, while nitrogen remains liquid in polar regions. The survival of life during these extreme glacial episodes represents one of the most remarkable examples of biological resilience in Earth's history. Marine ecosystems persist beneath the ice in environments completely isolated from atmospheric exchange and solar energy input. These refugial ecosystems depend entirely on chemical energy sources, hydrothermal vents, radioactive decay, and chemical reactions between seawater and oceanic crust, while waiting for conditions favorable to photosynthesis to return. Hydrothermal vent communities provide oases of warmth and chemical energy that maintain local ecosystems despite global freezing. The hot springs continue operating beneath kilometers of ice, creating convection currents that transport nutrients and dissolved chemicals through restricted circulation systems. Chemosynthetic bacteria convert hydrogen sulfide and methane into organic compounds, supporting food webs that remain completely independent of solar energy and surface conditions. The mystery of snowball termination puzzles climate scientists who model the mechanisms required to escape from global glaciation once established. The high albedo of ice-covered surfaces creates such effective cooling that even significant increases in atmospheric greenhouse gas concentrations may not provide sufficient warming to initiate widespread melting. Volcanic carbon dioxide emissions continue during glaciation, gradually increasing atmospheric concentrations over millions of years until greenhouse warming overcomes ice albedo cooling. The escape from snowball conditions occurs through rapid deglaciation once critical temperature thresholds are exceeded. Carbon dioxide concentrations may reach levels hundreds of times higher than modern atmospheric values before triggering significant ice melting. Once melting begins, the process accelerates through the same albedo feedbacks that created global glaciation, but operating in reverse as dark ocean surfaces replace reflective ice and snow. The deglaciation events create some of the most extreme environmental changes in Earth's history as the planet transitions from frozen wasteland to greenhouse hothouse within periods measured in thousands rather than millions of years. Meltwater floods carry enormous loads of glacial sediment into marine basins, while rapid weathering of fresh rock surfaces consumes atmospheric carbon dioxide faster than volcanic outgassing can replace it. These rapid transitions leave distinctive geological signatures that mark the termination of snowball episodes. Only took a few million years to freeze and thaw an entire planet through climate feedbacks that amplified small changes in solar energy balance into global environmental catastrophes, transitions that tested the limits of biological adaptation while creating evolutionary bottlenecks that influenced all subsequent life history. Only required precise timing between volcanic outgassing rates and weathering processes to accumulate sufficient atmospheric carbon dioxide for escaping from global glaciation without triggering runaway greenhouse effects. Only needed exactly the right orbital and rotational parameters to maintain stable ice sheets while preventing complete atmospheric collapse. The frozen Earth conducts its glacial experiments with the patient persistence of ice sheet dynamics operating over geological timescales. Ice accumulates gradually in polar regions before spreading toward lower latitudes as climate feedbacks amplify cooling trends. The glaciation proceeds episodically with advances and retreats that reflect complex interactions between orbital cycles, atmospheric composition, and continental configuration. These climatic oscillations create selection pressures that drive evolutionary innovations in cold tolerance and metabolic efficiency. Organisms develop antifreeze proteins that prevent ice crystal formation in cellular fluids, while maintaining biochemical function at temperatures far below normal physiological ranges. Others evolve dormancy strategies that allow survival through extended periods of environmental stress when normal metabolic activity becomes impossible. The biogeochemical consequences of global glaciation extend far beyond temperature effects to influence ocean chemistry, atmospheric composition, and nutrient cycling throughout marine and terrestrial ecosystems. Reduced weathering rates decrease the supply of dissolved minerals to ocean basins, while increased ice storage removes water from active hydrological cycling. The chemical composition of seawater changes as evaporation concentrates dissolved salts in unfrozen regions, while precipitation of mineral phases removes dissolved species from solution. Marine productivity collapses as ice coverage blocks solar radiation required for photosynthesis, while simultaneously creating physical barriers that prevent vertical mixing and nutrient transport. The reduced biological activity allows dissolved carbon dioxide concentrations to increase, while oxygen levels decline through respiratory consumption without photosynthetic replacement. These chemical changes create conditions favoring anaerobic metabolism and reducing biogeochemical processes. The recovery from snowball conditions triggers rapid reorganization of global ecosystems as environmental conditions change faster than most organisms can adapt through normal evolutionary processes. Surviving lineages undergo rapid evolutionary radiation to exploit newly available ecological niches, while extinct groups leave permanent gaps in ecosystem structure and function. The environmental disruption creates opportunities for evolutionary innovations that might never occur under stable climatic conditions. Ocean circulation patterns resume as ice melting re-establishes density gradients and thermal contrasts that drive large-scale water movements. The renewed circulation transports nutrients from deep storage reservoirs to surface waters where photosynthetic activity can resume. Chemical weathering accelerates as ice retreat exposes fresh rock surfaces to enhanced precipitation and temperature fluctuations that fragment mineral grains and increase surface area available for chemical attack. The post-glacial world emerges with altered continental configurations and ocean chemistry that reflects the extreme environmental conditions experienced during snowball episodes. Enhanced chemical weathering rates consume atmospheric carbon dioxide rapidly while delivering increased nutrient loads to marine ecosystems. The environmental recovery establishes new baseline conditions for continued evolution and ecosystem development. The Ediacaran biota emerge from the post-glacial seas like Earth's first tentative sketches of multicellular complexity. Soft-bodied organisms that resemble living quilts more than any creatures found in modern ecosystems. These enigmatic life forms appear in the fossil record around 180 million years ago, following the final snowball Earth episode. As if the extreme environmental stress triggered evolutionary experiments in new forms of biological organization. They grow as large as dinner plates while maintaining bodies so soft and pliable that fossilization occurs only under the most exceptional preservation conditions. Dickinsonia represents the most famous of these ancient creatures, reaching lengths of over a meter while displaying bilateral symmetry and segmented body plans that suggest sophisticated developmental control systems. The organism lacks obvious feeding structures, circulatory systems, or reproductive organs, creating puzzles about how such large multicellular bodies could function without the specialized tissues that characterize modern animals. Some paleontologists interpret the segmented pattern as evidence for true animal organization, while others suggest these creatures represent entirely different solutions to the challenges of multicellular life. The Ediacaran organisms colonize shallow marine environments with the quiet persistence of biological innovation, proceeding through trial and error over millions of years. Charnia grows like a fractal fern, branching repeatedly according to mathematical rules that maximize surface area while minimizing structural materials. Spriggina displays what appears to be a head region and jointed appendages, suggesting mobility and sensory capabilities despite preserving as simple impressions in sandstone. Tribrachidium exhibits threefold radial symmetry unlike any modern organism, rotating its feeding structures according to geometric principles that remain mysterious. These creatures construct their bodies from tissues so soft that they leave fossils only when buried rapidly by fine sediment under conditions that exclude oxygen and prevent bacterial decay. The preservation requires precise environmental conditions, calm water to prevent current disturbance, rapid sediment deposition to provide immediate burial, and anoxic conditions to inhibit decomposition. Most Ediacaran fossils preserve as impressions rather than true body fossils, recording the external morphology while providing limited information about internal anatomy or physiology. The feeding strategies of Ediacaran organisms remain largely mysterious due to the absence of obvious mouth openings, digestive systems, or specialized feeding appendages in most species. Some paleontologists propose that these creatures absorb nutrients directly through their body surfaces, functioning more like giant bacteria than conventional animals. Others suggest symbiotic relationships with photosynthetic microorganisms that provided energy through internal partnerships similar to modern corals and lichens. Recent biochemical analysis of Ediacaran fossils using organic geochemistry techniques provides new insights into their biological relationships and metabolic strategies. Cholesterol and other steroid compounds found in association with Dickinsonia fossils suggest animal-like metabolism, supporting interpretations that place these organisms within the early animal evolutionary tree. The molecular signatures indicate cell membrane compositions similar to modern animals while lacking the complex lipid molecules associated with bacterial or algal cells. The mystery of Ediacaran extinction puzzles evolutionary biologists who study the transition from these enigmatic soft-bodied forms to the hard-shelled animals that dominate Cambrian fossil assemblages. Most Ediacaran species disappear from the fossil record before the Cambrian explosion begins, suggesting either mass extinction or evolutionary transformation into forms with different preservation potential. The environmental changes associated with this transition include rising oxygen levels, changing ocean chemistry, and the evolution of predatory behaviors that may have made soft-bodied lifestyles unsustainable. Alternative hypotheses propose that Ediacaran organisms represent evolutionary experiments that failed to establish lasting lineages rather than direct ancestors of modern animals. The body plans and developmental patterns displayed by these creatures appear so different from conventional animal organization that they may represent entirely separate solutions to multicellular life that were eventually outcompeted by more efficient biological designs. The Ediacaran biota might represent an evolutionary dead end rather than a foundational phase in animal evolution. The global distribution of Ediacaran fossils indicates that these organisms colonized shallow marine environments on multiple continents during a relatively brief interval of geological time. Fossil localities in Australia, Russia, Namibia, and eastern North America preserve similar assemblages of soft-bodied creatures, suggesting that these life forms achieved worldwide distribution despite their apparent lack of hard skeletal elements or sophisticated locomotory capabilities. The sedimentary environments that preserve Ediacaran fossils provide insights into the ecological conditions that supported these ancient communities. Most fossils occur in shallow marine sandstones and siltstones that accumulated in calm water environments with minimal current activity. The fine-grained sediments suggest low-energy depositional settings where delicate organisms could thrive without constant physical disruption from waves or currents. Only took a few tens of millions of years for multicellular life to experiment with body plans and organizational strategies that would never be repeated in subsequent evolution, biological innovations that explored alternative solutions to the challenges of complex life while establishing foundations for more familiar forms of animal organization. Only required precisely the right environmental conditions to support large, soft-bodied organisms while providing exceptional preservation opportunities that allowed these delicate creatures to leave fossil evidence. Only needed evolutionary mechanisms sophisticated enough to coordinate multicellular development and maintain complex body plans without the hard skeletal elements that characterize most large organisms. The Ediacaran experiments proceed through their evolutionary trials with the methodical persistence of natural selection operating on biological innovations that have no modern analogues. Each species explores different solutions to the fundamental challenges of multicellular life nutrient acquisition, waste removal, structural support, and reproductive strategies while lacking the specialized organ systems that modern animals use to solve these same problems. These ancient communities establish new forms of ecological interaction that remain poorly understood due to preservation limitations and the absence of modern analogues for comparison. Some Ediacaran organisms appear to have lived as sessile filter feeders, extracting nutrients from water currents while remaining attached to seafloor substrates. Others may have been mobile deposit feeders that moved slowly across sediment surfaces while processing organic matter from bacterial mats and detrital materials. The reproductive strategies of Ediacaran organisms remain largely speculative due to the absence of preserved reproductive structures in most species. Some forms display evidence for budding or fragmentation as asexual reproductive mechanisms, while others show size distributions that might reflect sexual reproduction and larval development stages. The evolutionary transition from asexual to sexual reproduction may have occurred during this interval. Though direct evidence remains elusive, predator-prey relationships during the Ediacaran period appear to have been minimal compared to subsequent evolutionary periods, with most interactions involving competition for space and resources rather than active predation. The absence of obvious defensive structures, escape mechanisms, or predatory adaptations suggests that these communities operated according to ecological principles fundamentally different from modern marine ecosystems where predation plays a central organizing role. The environmental chemistry during Ediacaran time reflects the transition from predominantly anoxic to increasingly oxygenated ocean conditions that may have enabled the evolution of large multicellular organisms. Rising oxygen levels provided energy resources for more active metabolisms, while simultaneously creating oxidative stress that required new biochemical adaptations. The changing chemical conditions established environmental parameters that would constrain all subsequent animal evolution. The Ediacaran biota establish evolutionary precedents for complex multicellular organization while exploring biological solutions that remain unique in the history of life. These ancient experiments create developmental and ecological innovations that influence subsequent evolution, even though the specific lineages may not have survived the transition to Cambrian ecosystems. The soft-bodied communities represent biological creativity operating under environmental constraints that will never again occur in Earth's history. The Cambrian explosion begins with the sudden appearance of hard shells and skeletons in the fossil record, as if evolution simultaneously discovered the value of preserving its experimental results in mineral form. Around 540 million years ago, diverse animal lineages independently evolved the ability to precipitate calcium carbonate, calcium phosphate, and silica from seawater, creating durable body parts that transform the preservation potential of life on Earth. This biomineralization revolution produces the first comprehensive fossil record of complex animal diversity while fundamentally altering marine ecosystems through new predator-prey dynamics and ecological interactions. Trilobites become the most successful arthropods of the Paleozoic era, developing compound eyes with calcite lenses that provide sophisticated visual systems for navigating ancient seafloors. Their segmented bodies display remarkable diversity in form and function. Some species specialize in burrowing through sediment, while others evolve elaborate spines and defensive structures for protection against emerging predators. The trilobite body plan proves so successful that these organisms persist for nearly 300 million years, surviving multiple mass extinction events before finally disappearing at the end of the Permian period. The diversity of Cambrian animal forms exceeds anything seen in modern oceans, with body plans and anatomical innovations that appear suddenly in the fossil record without obvious evolutionary precursors. Opabinia displays 5 mushroom-shaped eyes and a bizarre feeding appendage that resembles a vacuum cleaner hose tipped with a grasping claw. Waiwaxia combines features that seem to blend characteristics of mollusks, annelids, and other major animal groups, creating taxonomic puzzles that persist despite decades of detailed anatomical study. Anomalocaris emerges as the ocean's first apex predator, reaching lengths of over 2 meters while pursuing prey with flexible swimming appendages and circular feeding structures lined with sharp spines. This giant arthropod represents a completely extinct body plan that combines features found in no modern organism, suggesting that early animal evolution explored morphological possibilities that were later abandoned as ecosystems matured and competitive interactions intensified. The Burgess Shale in British Columbia preserves exceptional soft tissue details that provide insights into Cambrian animal anatomy and ecology impossible to obtain from typical fossil assemblages. The fine-grained sediments capture not only hard shells and skeletons, but also muscles, digestive systems, and even bacterial biofilms that covered ancient seafloors. These exceptional preservation conditions create a paleontological laboratory where scientists can study complete ancient ecosystems rather than isolated skeletal elements. Hallucigenia challenges conventional understanding of animal body plans with its rows of defensive spines and enigmatic feeding appendages that originally led to reconstructions with the animal positioned upside down and backward. Detailed study reveals a sophisticated predator equipped with sharp claws for grasping prey and protective spines for deterring larger predators. The organism belongs to an extinct group related to modern velvet worms, suggesting that some Cambrian lineages have surviving descendants despite their bizarre ancestral forms. The evolution of predation during the Cambrian period drives an evolutionary arms race that produces increasingly sophisticated defensive structures and escape mechanisms. Shells and skeletons provide passive protection, while improved sensory systems and locomotory capabilities enable active predator avoidance. The ecological pressure of predation fundamentally restructures marine communities, eliminating vulnerable life forms while promoting innovations in defense, mobility, and sensory perception. The mystery of Cambrian diversification puzzles evolutionary biologists who attempt to explain how so many complex animal forms could appear simultaneously after billions of years of predominantly microbial evolution. The fossil record suggests that major animal phyla originated within a relatively brief interval of perhaps 20 million years, representing rapid evolutionary innovation that has no parallel in subsequent Earth history. This apparent acceleration may reflect preserved bias rather than true evolutionary tempo, as hard shells dramatically improve fossilization potential compared to soft-bodied predecessors. Molecular clock studies based on genetic differences between modern animal groups suggests that many evolutionary lineages actually diverged much earlier than their first fossil appearances indicate. The estimates place the origin of major animal groups hundreds of millions of years before the Cambrian period, implying a long period of cryptic evolution among soft-bodied ancestors that left no preserved fossil evidence. The Cambrian explosion may represent the evolution of fossilizable hard parts rather than the origin of animal diversity itself. Environmental changes during the pre-Cambrian-Cambrian transition create new ecological opportunities that may have triggered rapid evolutionary innovation. Rising atmospheric oxygen concentrations enable larger body sizes and more active metabolisms, while changing ocean chemistry facilitates biomineralization through enhanced calcium and silica availability. The environmental changes establish chemical conditions that support complex animal ecosystems for the first time in Earth's history. Only took a few tens of millions of years to establish all major animal body plans that persist through subsequent geological time, evolutionary innovations that explored morphological possibilities so thoroughly that later evolution focuses primarily on variations within established themes rather than entirely new organizational strategies. Only required precisely the right environmental conditions to support complex animal metabolism while providing chemical resources for biomineralization and fossilization. Only needed genetic and developmental mechanisms sophisticated enough to coordinate complex multicellular body plans while maintaining stable inheritance of anatomical innovations across generations. The Cambrian explosion proceeds through its diversification phase with the accelerated pace of evolutionary innovation operating under reduced competitive constraints in newly available ecological niches. Each major animal group establishes distinctive anatomical features and ecological strategies that define their evolutionary trajectory through subsequent geological periods. Arthropods develop jointed appendages and external skeletons that enable diverse locomotory and feeding strategies. Mollusks evolve muscular foot structures and protective shells that support both mobile and sessile lifestyles. These anatomical innovations establish modular body plans that prove remarkably evolvable over geological timescales while maintaining basic organizational principles that constrain morphological diversity within recognizable limits. The segmented arthropod body plan supports enormous diversity in appendage structure and function while preserving fundamental features of jointed limbs and external skeletons. Mollusk organization allows independent evolution of shells, locomotory systems, and feeding structures while maintaining basic body plans recognizable across hundreds of millions of years. The ecological consequences of Cambrian diversification extend beyond individual organism evolution to influence entire ecosystem structure and function. Predator-prey relationships become central organizing principles in marine communities as sophisticated hunting strategies drive corresponding innovations in defensive mechanisms and escape behaviors. The complexity of food web interactions increases dramatically as specialized feeding structures enable exploitation of diverse food resources and ecological niches. Bioturbation intensifies as burrowing organisms disturb seafloor sediments while searching for food and shelter, fundamentally altering sedimentary processes and biogeochemical cycling in marine environments. The mechanical mixing homogenizes chemical gradients that previously structured microbial communities while creating new microenvironments where different geochemical processes can operate. These changes influence preservation potential and create feedback effects that modify subsequent evolution. The biomineralization revolution establishes new biogeochemical cycles that link biological processes with ocean chemistry through the precipitation and dissolution of biogenic minerals. Calcium carbonate production by marine organisms begins to influence global carbon cycling, while silica extraction by diatoms and radiolarians affects dissolved silicon concentrations in seawater. These biological influences on ocean chemistry create feedbacks that constrain subsequent evolutionary innovation while establishing biogeochemical processes that operate through subsequent geological time. The Cambrian experimental phase establishes anatomical and ecological foundations that support all subsequent animal evolution while exploring morphological possibilities that remain unique in the fossil record. The diversity and disparity of Cambrian animal forms exceed those found in modern oceans, suggesting that early animal evolution operated under different constraints and opportunities than those that structure contemporary ecosystems. Land surfaces transform from barren rock to living landscapes as plants and fungi establish the first terrestrial partnerships, colonizing exposed continental margins with patient persistence that operates across geological timescales. The transition from aquatic to terrestrial environments requires evolutionary solutions to challenges that never existed in marine ecosystems: desiccation, gravitational stress, temperature fluctuations, and ultraviolet radiation exposure. Plants develop waxy cuticles and internal transport systems, while fungi create extensive underground networks that extract nutrients from weathering rock and decomposing organic matter. The earliest land plants resemble modern mosses and liverworts, lacking true roots, stems, or leaves, while maintaining dependence on water films for reproduction and nutrient transport. These primitive bryophytes colonize moist environments near shorelines and river valleys, forming thin carpets of photosynthetic tissue that gradually modify soil chemistry through organic acid production and mineral weathering. Their life cycles remain tied to aquatic conditions, as swimming sperm require water films to reach eggs, constraining early terrestrial vegetation to environments where surface moisture persists for extended periods. Fungi precede plants in the colonization of land surfaces, establishing extensive hyphal networks that penetrate rock crevices and extract nutrients from mineral weathering long before photosynthetic organisms develop terrestrial capabilities. These saprophytic organisms decompose any available organic matter while secreting acids that accelerate chemical weathering of silicate minerals. The fungal networks create primitive soil ecosystems that provide foundation substrates for subsequent plant colonization while establishing biogeochemical cycles that link biological and geological processes. The partnership between plants and fungi creates mycorrhizal relationships that prove essential for successful plant establishment in nutrient-poor terrestrial environments. Fungal hyphae extend plant root systems by orders of magnitude, accessing water and mineral nutrients from soil volumes far beyond direct root penetration. In exchange, plants provide fungi with photosynthetically produced organic compounds that fuel fungal growth and reproduction. These mutualistic relationships develop during the earliest stages of terrestrial ecosystem establishment and persist throughout subsequent plant evolution. Rhynia represents one of the best preserved early land plants, discovered in the 400-million-year-old Rhynie chert of Scotland, where exceptional fossilization conditions preserve cellular details of ancient terrestrial ecosystems. The plant displays simple branching stems with terminal sporangia but lacks true leaves or roots, obtaining nutrients through fungal partnerships and primitive transport systems. The fossil preservation includes fungi, bacteria, and even early terrestrial arthropods, providing comprehensive insights into ancient land ecosystem structure and function. The evolution of vascular tissue revolutionizes terrestrial plant architecture by enabling efficient transport of water and nutrients through plant bodies that can achieve substantial heights above ground level. Xylem tissue creates rigid tubes that conduct water upward from root systems while providing structural support against gravitational stress. Phloem tissue distributes photosynthetic products throughout the plant body, enabling specialization of different tissues for distinct functions like photosynthesis, nutrient acquisition, and reproduction. These transport innovations allow plants to escape their dependence on surface water films while exploiting aerial environments for photosynthesis and reproduction. Leaves evolve as specialized photosynthetic organs that maximize light capture while minimizing water loss through controllable stomatal pores. Root systems develop increasing complexity and depth penetration, accessing groundwater reserves and soil nutrients while providing anchorage for increasingly tall plant bodies. The mystery of plant terrestrialization timing remains contentious among paleontologists who study the earliest evidence for land-based photosynthesis. Molecular clock estimates suggest that major plant lineages diverged much earlier than their first definitive fossil appearances, implying extensive cryptic evolution in terrestrial environments that left minimal preserved evidence. Chemical biomarkers in ancient sediments hint at terrestrial plant activity hundreds of millions of years before convincing morphological fossils appear in the rock record. Spore assemblages provide indirect evidence for early terrestrial plant diversity and distribution, though interpreting spore morphology requires careful consideration of taphonomic processes and taxonomic relationships. The earliest spores display simple morphologies that could derive from aquatic or terrestrial parent plants, creating ambiguity about the timing and environmental context of plant terrestrialization. More complex spore types with distinctive sculptural features provide stronger evidence for terrestrial plant diversity during the Ordovician and Silurian periods. The atmospheric consequences of terrestrial plant evolution include significant modifications to global carbon cycling and oxygen production that influence climate and atmospheric composition over geological timescales. Land plants increase the efficiency of photosynthetic carbon fixation while creating new reservoirs for organic carbon storage in soils and plant tissues. Enhanced chemical weathering accelerates atmospheric carbon dioxide consumption through plant-mediated acid production and increased surface area exposure of silicate minerals. Only took several tens of millions of years to transform lifeless continental surfaces into complex terrestrial ecosystems, evolutionary innovations that required solving fundamental physiological challenges while establishing entirely new ecological relationships between organisms and their physical environment. Only needed precisely the right atmospheric composition to support photosynthesis while providing sufficient ozone protection against harmful ultraviolet radiation. Only required genetic and developmental mechanisms sophisticated enough to coordinate complex multicellular plant bodies while maintaining reproductive systems adapted to terrestrial conditions. The terrestrial colonization proceeds through its establishment phase with the methodical persistence of ecological succession operating over geological timescales as pioneer species modify environmental conditions in ways that facilitate subsequent colonization by more specialized organisms. Early plant communities create localized soil development through organic matter accumulation and enhanced chemical weathering while providing habitat and food resources for emerging terrestrial animal communities. These ecosystem engineering effects accelerate as plant diversity increases and terrestrial food webs develop increasing complexity and specialization. Herbivorous arthropods evolve to exploit plant tissues as food sources, while decomposer organisms process organic matter that accumulates in developing soil systems. The ecological interactions create positive feedbacks that enhance ecosystem stability and productivity while promoting continued evolution and diversification of terrestrial life forms. The geochemical consequences of plant terrestrialization extend beyond local soil development to influence global biogeochemical cycling through enhanced chemical weathering and modified hydrological processes. Plant transpiration increases atmospheric moisture content and influences precipitation patterns, while root systems alter groundwater flow and soil permeability. These hydrological changes affect erosion rates and sediment transport, while modifying the chemical composition of runoff reaching marine environments. Carbon cycling undergoes fundamental reorganization as terrestrial plant productivity begins to rival marine photosynthesis in global significance, while creating new pathways for organic carbon burial in terrestrial sedimentary environments. Lignin evolution in vascular plants produces organic compounds that resist bacterial decomposition, leading to accumulation of organic matter in swamp and wetland environments that will eventually become coal deposits. These carbon burial processes influence atmospheric carbon dioxide concentrations and global climate over geological timescales. The pedogenesis processes initiated by early terrestrial ecosystems establish soil formation mechanisms that operate throughout subsequent geological time, while creating increasingly complex chemical and physical environments that support diverse terrestrial communities. Soil development proceeds through interactions between biological, chemical, and physical processes that create distinct horizons and chemical gradients within developing soil profiles. Weathering accelerates under biological influence as plant roots and fungal hyphae penetrate rock crevices while secreting organic acids that enhance mineral dissolution rates. The biological weathering processes expose fresh mineral surfaces to chemical attack, while concentrating dissolved nutrients in soil solutions where they become available for biological uptake. These biogeochemical cycles establish nutrient cycling mechanisms that support terrestrial ecosystem productivity. The terrestrial experimental phase establishes ecological and biogeochemical foundations that support all subsequent land-based evolution, while creating environmental conditions that feed back to influence atmospheric composition and global climate systems that operate through subsequent geological time. Carboniferous swamps stretch across equatorial lowlands like vast botanical laboratories, conducting Earth's most ambitious experiment in carbon sequestration, as towering tree ferns and primitive conifers grow with unprecedented vigor in the warm, humid climate. These ancient forests achieve productivity levels that dwarf modern tropical ecosystems, converting atmospheric carbon dioxide into organic matter at rates that gradually lower global atmospheric concentrations while burying enormous quantities of plant material in waterlogged sediments that resist bacterial decomposition. The accumulated biomass will eventually transform into coal seams that power human civilization hundreds of millions of years in the future. Scale trees reach heights of 40 meters with trunks over a meter in diameter. Despite lacking the secondary growth mechanisms that enable modern trees to achieve comparable sizes, Lepidodendron and Sigillaria construct their massive stems from primary tissue alone, creating structural engineering solutions that have no modern analogues among large plants. The bark displays distinctive diamond-shaped scars where leaves attached directly to the main stem, creating fossilization patterns so characteristic that isolated bark fragments can be identified to species level after 300 million years of preservation. These ancient forests develop under atmospheric conditions radically different from those that constrain modern plant growth and ecosystem structure. Oxygen concentrations reach levels of 35% compared to today's 21%, creating atmospheric density that supports the evolution of giant flying insects while increasing fire hazard to levels that make modern forest management strategies impossible. Carbon dioxide concentrations fluctuate between very low levels during peak plant productivity and much higher levels during periods of reduced photosynthetic activity. The high oxygen atmosphere enables arthropods to achieve sizes impossible under modern atmospheric conditions, as passive diffusion through simple tracheal systems can supply oxygen to much larger body masses. Dragonflies with wingspans approaching 1 meter patrol the forest canopy, while millipedes over 2 meters long process fallen plant material on the forest floor. These giant arthropods represent evolutionary experiments in body size scaling that become impossible once atmospheric oxygen concentrations return to lower levels. Carboniferous plant reproduction relies entirely on spores and primitive seeds that require moist conditions for successful fertilization and early development. The sexual reproduction of these ancient plants depends on swimming sperm that navigate water films to reach eggs, constraining successful reproduction to environments where surface moisture persists for extended periods. This reproductive limitation keeps these highly productive forests restricted to lowland swamps and river valleys where water tables remain consistently high. The coal formation process begins in these ancient swamps as plant material accumulates faster than bacterial decomposition can process it, creating thick layers of organic matter that undergo gradual chemical transformation over geological time. Waterlogged conditions exclude oxygen and prevent complete organic matter breakdown while promoting the preservation of complex organic molecules like lignin and cellulose that form the chemical foundation of coal. The accumulating plant material subsides gradually under its own weight, while additional sediment layers bury the organic deposits. Diagenesis transforms the buried plant material through a series of chemical and physical changes that increase carbon concentration while removing oxygen and hydrogen through progressive heating and compression. Peat converts to lignite through loss of moisture and volatile compounds, then to bituminous coal through continued heating and pressure, and finally to anthracite through metamorphic processes that create nearly pure carbon with minimal impurities. Each stage of coal formation concentrates the solar energy originally captured by carboniferous photosynthesis into increasingly energy-dense solid fuels. The mystery of carboniferous productivity puzzles plant physiologists who study the factors that enabled such extraordinary plant growth rates in ancient forest ecosystems. The combination of high atmospheric carbon dioxide during some intervals, elevated temperatures, and abundant moisture created optimal conditions for photosynthesis, while the absence of herbivorous mammals allowed plant communities to allocate resources entirely to growth and reproduction rather than defensive compounds and structures. Alternative explanations focus on atmospheric pressure and composition effects that could have enhanced photosynthetic efficiency through improved gas exchange and reduced photorespiration. Higher atmospheric density may have facilitated carbon dioxide diffusion into plant tissues, while elevated oxygen concentrations could have enhanced respiratory energy production. The unique atmospheric conditions created experimental opportunities for plant physiology that have never been repeated in subsequent Earth history. The global distribution of carboniferous coal deposits indicates that productive swamp forests developed across multiple continents during this period, suggesting that climate conditions favoring rapid plant growth and organic matter preservation operated at global scales. Coal seams occur in North America, Europe, Asia, and Australia, reflecting the widespread development of lowland forest ecosystems during the late Paleozoic era. The temporal correlation of coal formation across different continents suggests global climate control rather than local environmental factors. Only took several tens of millions of years to convert atmospheric carbon dioxide into buried organic matter that would fuel technological civilization, an unintended consequence of plant evolution and atmospheric chemistry that concentrated millions of years of captured solar energy into accessible fossil fuel deposits, only required precisely the right combination of atmospheric composition, climate conditions, and depositional environments to enable rapid plant growth while preventing organic matter decomposition. Only needed geological processes that could preserve and transform organic matter over hundreds of millions of years while maintaining accessibility for future extraction. The Carboniferous forests conduct their carbon cycling experiments with the industrious persistence of plant productivity, operating under atmospheric conditions that enhance photosynthetic efficiency while restricting decomposer activity through waterlogged soil conditions. Each growing season converts enormous quantities of atmospheric carbon dioxide into plant tissues, while the seasonal leaf fall contributes organic matter to accumulating peat deposits that resist bacterial breakdown. These carbon burial processes fundamentally alter global atmospheric composition as plant productivity removes carbon dioxide faster than volcanic outgassing and weathering processes can replace it. The atmospheric carbon dioxide concentration declines gradually over millions of years as organic carbon accumulates in sedimentary deposits, rather than returning to atmospheric reservoirs through respiration and decomposition. This drawdown contributes to global cooling trends that eventually trigger ice age conditions during the later Carboniferous period. The biogeochemical consequences of Carboniferous plant productivity extend beyond carbon cycling to influence nitrogen, phosphorus, and sulfur, cycling through enhanced organic matter production and burial. Plant uptake concentrates these nutrients in organic tissues that become incorporated into sedimentary deposits rather than recycling through marine ecosystems. The nutrient sequestration may have contributed to reduced marine productivity during intervals of maximum terrestrial plant growth. Wetland chemistry in Carboniferous swamps creates unique preservation conditions that maintain organic matter integrity while preventing complete anaerobic decomposition. The chemical environment remains acidic and oxygen depleted while containing sufficient dissolved nutrients to support continued plant growth. These conditions favor the preservation of resistant organic molecules, while promoting the breakdown of more labile compounds that would otherwise support extensive microbial communities. The hydrological conditions in Carboniferous swamps maintain stable water levels that prevent alternating wet-dry cycles that would enhance organic matter decomposition through periodic oxygen exposure. The consistent waterlogging creates chemical stratification within sediment profiles, as oxygen consumption exceeds resupply from surface waters. These anoxic conditions preserve organic matter while promoting chemical reactions that enhance carbon concentration in buried plant materials. Sediment accumulation rates in productive swamp environments must balance organic matter production with subsidence rates to maintain optimal water depths for continued forest growth. Too rapid subsidence creates water depths that exclude terrestrial vegetation, while insufficient subsidence allows organic matter accumulation above water level where aerobic decomposition can proceed. The delicate balance between plant productivity, organic matter burial, and basin subsidence determines the thickness and continuity of coal seam development. The Carboniferous experimental phase establishes biogeochemical processes that influence global carbon cycling and atmospheric composition while creating fossil fuel resources that will eventually power technological civilization and influence global climate through anthropogenic carbon dioxide emissions that reverse the ancient carbon burial processes. Mass extinctions punctuate Earth's experimental timeline like laboratory accidents that clear entire sets of running experiments, eliminating established species and ecosystems while creating vacant ecological niches for surviving lineages to explore through evolutionary radiation. These catastrophic events occur at irregular intervals throughout geological history, each triggered by different combinations of environmental stresses that overwhelm the adaptive capacity of existing organisms, while paradoxically accelerating evolution among survivors who inherit depleted but opportunity-rich ecosystems. The end Permian extinction eliminates over 90% of marine species and 70% of terrestrial vertebrates, representing the most severe biological crisis in Earth's history as ecosystems collapse across multiple environments simultaneously. Massive volcanic eruptions in Siberia release enormous quantities of carbon dioxide, sulfur compounds, and toxic metals into the atmosphere while triggering rapid climate warming and ocean acidification. The environmental changes proceed faster than most organisms can adapt, creating selection pressures that favor only the most physiologically tolerant and ecologically flexible species. Volcanic winter effects from sulfur aerosols temporarily cool global climate, while ash clouds block solar radiation and disrupt photosynthesis across terrestrial and marine ecosystems. The cooling phase lasts for years to decades before greenhouse warming from accumulated carbon dioxide creates the opposite extreme of elevated temperatures and enhanced evaporation rates. These rapid oscillations between cooling and warming stress organisms adapted to stable climate conditions while favoring species capable of surviving extreme environmental variability. Ocean chemistry undergoes dramatic changes as carbon dioxide absorption creates acidic conditions that dissolve carbonate shells and skeletons, while hydrogen sulfide production in anoxic deep waters creates toxic conditions that eliminate most marine life. The chemical changes propagate through marine food webs as primary producers collapse and nutrient cycling breaks down. Surviving marine organisms must tolerate conditions that would be immediately lethal to most modern species while competing for limited resources in devastated ecosystems. The recovery from mass extinction proceeds through predictable ecological succession as surviving species undergo rapid evolutionary diversification to exploit vacant ecological niches left by extinct lineages. Small body size and generalized feeding strategies prove advantageous during extinction intervals, while specialized adaptations become liabilities when environmental conditions change rapidly. The survivors often represent evolutionary lineages that were previously minor components of pre-extinction ecosystems. Disaster taxa dominate post-extinction ecosystems as opportunistic species achieve temporary ecological success before being replaced by more specialized forms that evolve from surviving lineages. These disaster species often display rapid growth rates, broad environmental tolerances, and simple ecological requirements that enable quick colonization of disturbed environments. Their temporary success creates breathing room for more complex evolutionary innovations to develop among surviving lineages. The Cretaceous-Paleogene extinction eliminates non-avian dinosaurs along with marine reptiles, ammonites, and many plant species when an asteroid impact creates global environmental disruption that exceeds the tolerance limits of large-bodied organisms. The impact generates massive quantities of dust and debris that block solar radiation for months while triggering acid rain, wildfires, and tsunami damage across global scales. The sudden environmental change eliminates organisms dependent on consistent resource availability while favoring species capable of surviving extended periods of environmental stress. Impact winter conditions create selection pressures that favor small body size, omnivorous feeding strategies, and behavioral flexibility among surviving vertebrates. Mammals inherit ecological niches previously occupied by dinosaurs, while flowering plants replace gymnosperm-dominated vegetation in many terrestrial ecosystems. The ecological reorganization proceeds over millions of years as evolutionary innovations fill ecological roles that were eliminated by the extinction event. The mystery of extinction selectivity puzzles paleontologists who study the patterns of survival and extinction across different taxonomic groups and ecological strategies. Some extinctions appear to eliminate species randomly with respect to their ecological adaptations, while others show clear selectivity for particular body sizes, feeding strategies, or physiological tolerances. The selectivity patterns provide insights into the environmental stresses that caused each extinction while revealing the adaptive strategies that promote survival during catastrophic events. Body size proves to be a crucial factor in extinction survival, as large-bodied organisms typically experience higher extinction rates than small-bodied species during most mass extinction events. Large organisms require more resources and longer generation times, while displaying lower population sizes and reduced genetic diversity that limit their ability to adapt to rapidly changing conditions. Small organisms can maintain larger population sizes and shorter generation times that facilitate rapid evolutionary responses to environmental stress. Geographic distribution influences extinction risk, as widespread species with diverse habitat requirements typically survive mass extinctions better than endemic species with restricted geographic ranges or specialized ecological requirements. The pattern suggests that environmental heterogeneity provides refuge environments where local populations can survive regional environmental disruption. Species with broad geographic distributions have higher probabilities of maintaining viable populations in refuge areas. Only took a few 100,000 to several million years to eliminate most existing species, while setting up conditions for rapid evolutionary diversification among survivors, ecological catastrophes that compress normally gradual evolutionary processes into brief intervals of intense selection and adaptation. Only required environmental changes that exceeded the tolerance limits of existing organisms while maintaining sufficient refugia for some lineages to survive and diversify. Only needed extinction mechanisms that were severe enough to eliminate dominant species while leaving ecological opportunities for previously marginal lineages to explore. Mass extinctions conduct their evolutionary experiments with the devastating efficiency of environmental catastrophe operating over timescales that span multiple generations but remain brief compared to normal species durations. Each extinction event creates unique combinations of environmental stresses that test different aspects of organismal adaptation while eliminating ecological strategies that prove inadequate for survival under extreme conditions. These catastrophic selections establish new evolutionary baselines as surviving lineages undergo adaptive radiation to exploit ecological opportunities created by the elimination of competing species. The post-extinction diversification often produces evolutionary innovations that would have been impossible in pre-extinction ecosystems where established species occupied most available ecological niches. The ecological release enables rapid morphological and physiological evolution among survivors. The biogeochemical consequences of mass extinctions include fundamental reorganization of nutrient cycling and ecosystem function, as established ecological relationships collapse and new associations develop among surviving organisms. Primary productivity may decline dramatically during extinction intervals before recovering through different ecological pathways that reflect the taxonomic composition of surviving species rather than pre-extinction ecosystem structure. Marine ecosystems typically require longer recovery times than terrestrial systems due to their greater taxonomic losses and more complex food web structures that depend on specialized relationships between primary producers and consumers. The recovery may require millions of years to restore previous levels of biodiversity and ecosystem complexity while exploring new evolutionary solutions to ecological challenges. Climate feedbacks during extinction intervals can amplify environmental stress through positive feedback mechanisms that accelerate environmental change beyond the tolerance limits of additional species. Ecosystem collapse reduces biological carbon fixation while increasing carbon dioxide emissions through decomposition of dead organic matter. The feedbacks can maintain harsh environmental conditions for extended periods while preventing rapid ecosystem recovery. The evolutionary legacy of mass extinctions extends far beyond the immediate biological losses to influence subsequent evolution through the ecological and genetic bottlenecks that constrain post-extinction diversification. The survivors carry reduced genetic diversity that limits evolutionary potential, while the ecological simplification provides opportunities for evolutionary innovation that would not occur under more competitive conditions. Nervous systems develop from simple chemical signaling networks into sophisticated information processing architectures that eventually enable organisms to contemplate their own existence within Earth's grand experimental design. The evolution of consciousness emerges through incremental improvements in neural complexity and integration, beginning with basic stimulus-response mechanisms in primitive organisms and gradually elaborating into the self-aware intelligence that now studies the planet's 4-billion-year history of biological innovation and environmental change. Cnidarians like jellyfish established the first neural networks as diffuse arrangements of interconnected nerve cells that coordinate swimming movements and feeding responses without central command structures. These primitive nervous systems operate through simple electrical and chemical signaling that enables rapid communication between distant body regions while maintaining the decentralized organization that characterizes early animal neurology. Each nerve cell responds to local stimuli while contributing to coordinated behaviors that emerge from collective neural activity rather than hierarchical control. Bilateral symmetry drives the evolution of increasingly centralized nervous systems as organisms develop distinct head and tail regions that require different sensory and motor capabilities. The concentration of sensory organs in anterior body regions promotes neural centralization to reduce signal transmission delays between sensory input and motor output. This cephalization process establishes the basic architecture that will eventually support complex cognition through elaboration of anterior neural processing centers. Arthropods develop sophisticated compound eyes and complex behavioral repertoires that demonstrate remarkable information processing capabilities despite relatively small brain sizes. Dragonflies execute aerial hunting maneuvers that require precise visual tracking and predictive motor control, while social insects coordinate colony activities through chemical communication and spatial memory systems. These achievements suggest that neural complexity, rather than absolute brain size, determines cognitive capabilities in invertebrate nervous systems. The vertebrate nervous system evolves through elaboration of the basic caudate neural tube into increasingly complex brain structures that support diverse cognitive functions and behavioral capabilities. Fish develop specialized brain regions for processing visual, auditory, and chemical sensory information while maintaining sophisticated spatial navigation and social recognition abilities. Amphibians and reptiles add limbic system components that enhance emotional processing and learning, while supporting more complex behavioral responses to environmental stimuli. Birds achieve remarkable cognitive sophistication through convergent evolution of brain structures that parallel mammalian neural organization while employing different anatomical arrangements and cellular architectures. Corvids and parrots demonstrate tool use, problem-solving abilities, and social cognition comparable to primates, despite having evolved these capabilities independently through distinctly avian neural evolution. The convergent cognitive abilities suggest that intelligence represents a general solution to ecological challenges rather than a uniquely mammalian evolutionary innovation. Mammalian brain evolution explores increasing neural complexity through cortical expansion and elaboration while maintaining the basic vertebrate brain organization inherited from earlier evolutionary stages. The neocortex develops as an additional processing layer that enables more sophisticated analysis of sensory information and more flexible behavioral responses, while integrating with subcortical structures that control basic physiological and emotional functions. This neural architecture supports the cognitive flexibility that enables mammals to exploit diverse ecological niches and develop complex social behaviors. Primate evolution demonstrates progressive neural elaboration through increased brain size relative to body mass and enhanced connectivity between different brain regions that support more sophisticated cognitive integration and behavioral control. Social complexity drives much of this neural evolution, as group living requires individual recognition, alliance formation, and sophisticated communication that exceed the cognitive demands faced by solitary organisms. The social brain hypothesis suggests that intelligence evolved primarily to navigate complex social relationships rather than to solve environmental challenges. The mystery of consciousness emergence challenges neuroscientists and philosophers who attempt to understand how subjective experience arises from objective neural processes. The hard problem of consciousness involves explaining how electrical and chemical signaling in neural networks creates the qualitative, subjective aspects of mental experience that distinguish conscious awareness from unconscious information processing. Current neuroscience can identify neural correlates of consciousness, but cannot fully explain the causal mechanisms that generate subjective experience from brain activity. Self-awareness represents an additional cognitive capability that enables organisms to recognize themselves as distinct entities separate from their environment and other individuals. Mirror self-recognition tests reveal that only a few species demonstrate clear evidence for self-awareness, including great apes, elephants, dolphins, and some birds. This cognitive ability appears to require sophisticated neural integration that enables organisms to construct internal models of themselves as objects in the external world. Human consciousness achieves unprecedented sophistication through language capabilities that enable abstract thought, cultural transmission, and cumulative knowledge accumulation across generations. Symbolic communication allows human minds to manipulate concepts that have no direct physical reference while sharing complex ideas through spoken and written language. This symbolic processing capability enables human consciousness to transcend immediate sensory experience and contemplate abstract concepts like geological time, evolutionary history, and cosmic scale phenomena. Only took several 100 million years to evolve from simple stimulus response mechanisms to self-aware intelligence capable of understanding its own evolutionary origins, cognitive innovations that required precise coordination between sensory systems, motor control, memory storage, and information integration while maintaining the basic physiological functions necessary for survival. Only needed exactly the right evolutionary pressures to favor increasing neural complexity while providing sufficient environmental stability for cognitive evolution to proceed through cumulative improvements over geological timescales. Only required genetic and developmental mechanisms sophisticated enough to construct complex neural architectures while maintaining reliable information processing across individual lifespans and evolutionary timescales. Consciousness evolves through its developmental phases with the methodical persistence of neural evolution, operating over timescales that encompass millions of generations, while creating cognitive capabilities that enable individual organisms to understand processes operating over geological and cosmic timescales. Each increment in neural complexity enables new forms of information processing and behavioral control, while maintaining compatibility with previously evolved neural functions and physiological constraints. These cognitive innovations establish new forms of environmental interaction that transcend simple stimulus response mechanisms to include predictive modeling, abstract reasoning, and intentional environmental modification. Conscious organisms can anticipate future conditions and modify current behaviors to achieve desired outcomes while learning from past experiences and applying general principles to novel situations. The cognitive flexibility enables rapid behavioral adaptation that can proceed faster than genetic evolution while complementing rather than replacing basic evolutionary processes. The ecological consequences of consciousness include the development of technological capabilities that enable organisms to modify environmental conditions on scales comparable to geological processes while operating over timescales orders of magnitude shorter than typical evolutionary change. Conscious manipulation of fire, agriculture, and industrial processes creates environmental changes that influence global biogeochemical cycles and ecosystem structure while providing feedback that affects the evolutionary trajectory of the conscious organisms themselves. Cultural evolution emerges as a new form of information transmission that operates through learning and imitation rather than genetic inheritance while achieving rates of change that far exceed biological evolution. Conscious organisms can accumulate knowledge across generations while developing technologies and social institutions that modify selection pressures acting on their own species and other organisms. This cultural evolution creates novel evolutionary dynamics that operate through mechanisms unknown in pre-conscious biological systems. The reflexive capability of consciousness enables organisms to study their own evolutionary origins and understand their position within Earth's experimental timeline while contemplating their role as both products and agents of ongoing evolutionary change. This self-understanding creates ethical and practical responsibilities that have no precedent in unconscious evolutionary processes while providing opportunities for conscious participation in directing future evolutionary trajectories. Conscious organisms become capable of understanding Earth's 4 billion-year experimental history while recognizing their own emergence as the universe's first known attempt at self-understanding through the evolution of matter into patterns complex enough to contemplate their own existence and origins. The experimental protocols continue their operation beneath starlit skies as modern Earth maintains the same fundamental processes that have guided planetary evolution for billions of years, still testing new combinations of matter and energy while consciousness observes and occasionally influences the ongoing trials. The laboratory remains active, though its current experiments proceed with such gradual pacing that individual human lifespans capture only brief moments in extended geological investigations that span millions of years. Plate tectonics still rearranges continental configurations, while atmospheric and oceanic chemistry evolves through subtle variations that accumulate into significant changes over timescales that dwarf recorded human history. Climate oscillations between glacial and interglacial periods represent ongoing experiments in planetary temperature regulation as orbital cycles interact with atmospheric composition and ocean circulation patterns to produce environmental variations that test biological adaptation and ecosystem resilience. Ice sheets advance and retreat across northern continents with mathematical precision determined by celestial mechanics, while biological communities migrate, adapt, or face extinction according to their tolerance for changing conditions. These climate experiments operate with the same methodical persistence that characterized earlier geological investigations, though their current parameters reflect atmospheric and oceanic chemistry modified by 4 billion years of biological evolution. Evolution continues its patient exploration of biological possibilities as natural selection operates on genetic variation within populations while creating new species and eliminating others according to environmental pressures that change gradually over ecological and evolutionary timescales. The mechanisms remain fundamentally unchanged from those that produced the first cellular experiments billions of years ago, though they now operate within ecosystems of unprecedented complexity and diversity. Random mutations still provide raw material for natural selection, while ecological interactions create selection pressures that shape organismal form and function through the same trial and error processes that characterized earlier evolutionary investigations. Biogeochemical cycles maintain their ancient rhythms as carbon, nitrogen, phosphorus, and sulfur move between geological, atmospheric, oceanic, and biological reservoirs through pathways established during the planet's earliest experiments in chemical cycling. Photosynthesis still converts atmospheric carbon dioxide into organic matter, while respiration returns carbon to atmospheric reservoirs, maintaining the same basic chemical transformations that began with cyanobacterial innovations billions of years ago. Ocean circulation continues to distribute heat and chemical constituents around the globe, while weathering processes break down continental rocks and transport dissolved minerals to marine environments. The deep Earth engine continues its operation as radioactive decay provides energy for mantle convection that drives plate tectonics and volcanic activity according to physical principles that have remained constant throughout Earth's history. Magma generation and eruption still follow the same thermodynamic laws, while mineral crystallization proceeds according to temperature and pressure conditions that create igneous rocks with compositions determined by chemical equilibria, unchanged since the planet's formation. The internal heat that powers these processes represents the same energy source that drove geological activity during the Hadean and Archean eons. Hydrothermal systems maintain their role as chemical laboratories, where heated water interacts with rock under pressure conditions that promote mineral dissolution and precipitation, while creating environmental gradients that support chemosynthetic organisms dependent on chemical energy rather than solar radiation. These modern hydrothermal environments operate according to the same physical and chemical principles that characterized ancient systems, while supporting biological communities that utilize metabolic pathways inherited from Earth's earliest life forms. The chemical reactions proceed with the same thermodynamic driving forces that operated billions of years ago. Atmospheric composition continues to evolve through interactions between biological, geological, and chemical processes that maintain dynamic equilibria between production and consumption of trace gases while responding to perturbations from volcanic eruptions, biological activity, and human industrial processes. Oxygen and carbon dioxide concentrations fluctuate around baseline values determined by the balance between photosynthesis and respiration, while trace gases influence atmospheric chemistry through photochemical reactions driven by solar radiation. These atmospheric experiments proceed through the same chemical mechanisms that have operated throughout Earth's history. Ocean chemistry maintains its buffering capacity through carbonate equilibria and biological processes that regulate pH and nutrient concentrations while responding to inputs from rivers, atmospheric deposition, and hydrothermal vents according to chemical principles unchanged since the first oceans formed. Marine organisms still precipitate calcium carbonate shells and skeletons, while others extract silica from seawater to construct protective structures. Continuing the biomineralization experiments that began during the Cambrian explosion. The chemical processes follow the same thermodynamic laws while operating within marine ecosystems of vastly greater complexity and diversity. The mystery of future experimental directions remains hidden within the complex dynamics of Earth system interactions that involve feedbacks between climate, geology, biology, and human activities operating over multiple timescales from years to millions of years. Climate models attempt to predict future environmental conditions, while evolutionary biology explores potential trajectories for continued biological diversification under changing environmental conditions. The experimental outcomes depend on initial conditions and parameter values that cannot be determined with sufficient precision to enable accurate long-term predictions. extinction and origination rates fluctuate around background levels as species continue to appear and disappear through normal evolutionary processes, while occasional catastrophic events create temporary spikes in extinction rates that trigger subsequent evolutionary radiations among surviving lineages. These ongoing experiments in biological diversity follow the same patterns that characterized earlier mass extinctions and recovery periods, while operating within ecosystems that include conscious observers capable of documenting and potentially influencing the experimental outcomes. Only requires continued operation of physical, chemical, and biological processes that have functioned reliably for billions of years to maintain Earth's experimental capacity, while exploring new parameter combinations through natural variation and occasional catastrophic perturbations that reset ecosystem organization. Only needs the same fundamental forces and energy sources that have powered planetary evolution since formation to continue testing biological and geological innovations through trial and error processes operating over geological timescales. Only demands the same laws of physics and chemistry that have governed Earth system behavior throughout its history to support continued experimentation in complexity and organization. The planetary laboratory operates through its current experimental phase with the quiet persistence of natural processes that function continuously despite their imperceptible pace when viewed from human temporal perspectives. Geological processes reshape surface topography, while biological evolution explores new ecological strategies, and technological consciousness develops capabilities for understanding and potentially directing experimental parameters. The investigations continue with no predetermined endpoint or final objective beyond the exploration of possibilities within the constraints imposed by physical laws and available energy sources. These modern experiments proceed with the same methodical approach that characterized earlier geological and biological investigations, while incorporating new variables introduced by technological civilization and conscious environmental manipulation. The outcomes remain unpredictable, despite improved understanding of underlying processes, because complex system behavior emerges from interactions between multiple components, operating over different timescales with nonlinear feedbacks that amplify small perturbations into system-wide changes. Earth's experimental timeline extends into an indefinite future, as ongoing processes continue their exploration of matter and energy organization, while consciousness observes and gradually develops the capacity to participate consciously in directing experimental parameters toward desired outcomes. The experiments settle into their quietest rhythms now, operating beneath the vast indifference of cosmic time, where million-year cycles register as momentary fluctuations in processes that began before memory and continue beyond imagination. The laboratory grows still around its ongoing investigations, though stillness here means only the imperceptible pace of geological change and evolutionary drift rather than any cessation of the fundamental work. Tectonic plates continue their patient migration across the planetary surface, moving at speeds measured in centimeters per year while carrying continents through configurations that will not complete their transformations for hundreds of millions of years. The movements proceed with such gradual persistence that individual mountain ranges rise and erode away between major continental rearrangements, each topographic feature representing a brief experiment in crustal dynamics that leaves its signature in sedimentary layers before returning to the recycling systems that have operated since the first solid crust formed. Atmospheric molecules drift through their chemical cycles at speeds determined by wind patterns and photochemical reaction rates, while maintaining the gaseous equilibria that support complex life through processes so reliable they escape conscious notice despite their essential role in enabling every breath and heartbeat. The invisible chemistry continues its ancient work of transforming solar energy and mineral nutrients into biological structures, while removing metabolic wastes through oxidation reactions that return elements to their inorganic reservoirs. Ocean currents maintain their circulation patterns according to temperature and density gradients that distribute heat and dissolve substances around the globe, while marine organisms conduct their microscopic experiments in survival and reproduction within water that has traveled these same pathways for millions of years. The currents carry chemical signatures of volcanic activity and continental weathering while supporting biological productivity that converts inorganic nutrients into living tissue through photosynthetic processes, fundamentally unchanged since their invention billions of years ago. Deep within the planet's interior, radioactive decay continues to release energy that drives convection and magnetic field generation while following exponential decay laws that will operate unchanged until the last unstable nuclei have transformed into stable configurations. The energy flows upward through rock and magma according to physical principles that have remained constant since planetary formation, while powering surface processes that shape landscapes and influence climate through mechanisms that connect the planet's deepest interior with its atmospheric envelope. The biological experiments continue their patient exploration of ecological possibilities as populations fluctuate around, carrying capacities determined by resource availability and environmental conditions, while genetic variation provides raw material for evolutionary responses to changing selection pressures. Each generation tests slightly modified combinations of inherited traits while contributing to population-level changes that accumulate over evolutionary time into new species and ecological relationships. Consciousness observes these processes with increasing understanding while developing technologies that may eventually enable conscious participation in directing some experimental parameters. Though the scale and complexity of Earth system interactions suggest that human influence will remain a minor perturbation within much larger natural cycles. The observations themselves represent a new type of experiment, as matter organized into neural networks becomes capable of studying its own organization and history. The starlit sky rotates overhead with clockwork precision determined by planetary rotation and orbital mechanics, while distant galaxies continue their recession according to cosmic expansion that began with the universe itself. The Earth laboratory operates within this larger cosmic context as a temporary concentration of matter and energy that has achieved sufficient complexity to support self-aware investigation of its own experimental history. All processes settle toward their deepest rhythms as consciousness fades and natural cycles continue their work in the darkness. The experiments require no oversight or conscious direction to maintain their operation through geological time. They proceed with the patient persistence of physical law, operating on matter and energy within the constraints that have shaped planetary evolution since formation. The laboratory grows quiet around its ongoing investigations, while time continues its passage at scales that dwarf individual awareness. The work continues in silence and darkness, testing new combinations, exploring possibilities, maintaining the ancient protocols that have guided Earth's experimental timeline for 4 billion years. The experiments continue. The testing never ends. The results accumulate in sedimentary layers and fossil records, while new investigations begin in every generation of organisms and every cycle of geological activity. Sleep now. The laboratory runs itself. The work continues in the depths of time where consciousness cannot follow, but where the fundamental experiments in matter and complexity proceed with eternal patience toward outcomes that remain forever unpredictable within processes that operate with absolute reliability. The test continues quietly under starlit skies.